Since the first humans gazed upward into the darkness of night, stars have whispered to us across the void. Every ancient civilization wove stories around these distant lights. The Greeks saw heroes and monsters frozen in constellations. The Egyptians aligned their pyramids to stellar pathways, and the Polynesians navigated vast oceans, using stars as their only guide. Tonight, we journey through the complete story of these celestial beacons, from their gentle births in cosmic clouds to their dramatic endings that seed the universe with the very atoms that make up your body. Let the stars carry you into peaceful dreams. Far from the glittering lights of any city, far from even the soft glow of our own sun, there exist vast regions of space where darkness holds dominion. These are the molecular clouds, sometimes called stellar nurseries, and they are among the most peaceful places in all the cosmos. Stretching across dozens or even hundreds of light years, these clouds drift through the galaxy like great silent ships sailing an ocean of emptiness. Within their depths, something miraculous slowly unfolds the birth of stars. Picture, if you will, a cloud so enormous that light itself takes years to cross from one side to the other. This cloud is composed primarily of hydrogen, the simplest and most abundant element in the universe. Mixed within this hydrogen are traces of helium, left over from the earliest moments after the Big Bang, along with tiny grains of cosmic dust particles smaller than the width of a human hair, yet essential to the processes that will eventually create new suns. The temperature within these clouds hovers just a few degrees above absolute zero, around minus 260 degrees Celsius, making them among the coldest places in existence. For millions of years, such a cloud might drift peacefully through interstellar space, its particles moving so slowly in the frigid darkness that they barely interact with one another. The cloud maintains a delicate equilibrium, with the outward pressure of its gas balanced against the gentle, persistent pull of its own gravity. This balance could theoretically last forever, but the universe rarely allows such perfect stillness to persist indefinitely. Something eventually disturbs this cosmic tranquility. Perhaps a nearby star explodes in a supernova, sending shockwaves rippling through space at thousands of kilometers per second. Perhaps the cloud drifts too close to a spiral arm of its host galaxy, where the gravitational influence of millions of stars creates compression waves that squeeze the gas. Or perhaps two clouds collide in the darkness, their combined mass finally tipping the scales in favor of gravity. Whatever the trigger, the result is the same portions of the cloud begin to collapse inward upon themselves. This collapse happens with almost imperceptible slowness at first. The particles of gas and dust begin drifting toward regions of slightly higher density, drawn by gravitational attraction, so weak that it would take millions of years to move a single atom the distance of a city block. Yet this weakness is deceptive, for gravity is patient beyond human comprehension. It never tires, never wavers, and never ceases its gentle pulling. Over timescales that dwarf the entire history of human civilization, this persistence transforms diffuse clouds into dense cores. As material accumulates in these collapsing regions, something interesting begins to happen. The gas and dust do not simply fall straight inward. Instead, they begin to spiral, creating a rotating disk of material around the densest central point. This rotation is a consequence of angular momentum, a property of moving matter that the universe conserves with absolute fidelity. Even the tiniest initial rotation of the original cloud becomes amplified as the collapse proceeds, much like a figure skater spinning faster as they draw their arms close to their body. At the center of this swirling disk, pressure and temperature begin to rise. The gravitational energy released by the infalling material converts to heat, warming the core from those frigid temperatures near absolute zero to something more substantial. The central object, not yet a star, but no longer simply a cloud, enters a phase astronomers call a protostar. This protostar continues to grow as material from the surrounding disk spirals inward, feeding the hungry young object at the center. The journey from initial collapse to protostar takes roughly 100,000 years, a mere heartbeat in cosmic terms, yet still a span of time so vast that hundreds of human generations could live and die, while a single star takes its first tentative steps toward existence. During this period, the protostar remains hidden from view, shrouded within its cocoon of gas and dust. Only infrared telescopes, capable of detecting heat radiation that passes through this obscuring material, can reveal these stellar embryos to our curious eyes. Within the protostar, conditions grow increasingly extreme. The temperature at the core climbs steadily, 1,000 degrees, 10,000 degrees, 100,000 degrees. The pressure mounts as well, as the weight of all that accumulated material presses down upon the center with ever-increasing force. The hydrogen atoms, once drifting lazily through the cold darkness of the molecular cloud, now zip about at tremendous speeds, colliding with one another billions of times each second. Yet even at these elevated temperatures, the protostar has not truly become a star. For that transformation to occur, the core must reach approximately 10 million degrees Celsius, the threshold at which hydrogen nuclei can overcome their mutual electrical repulsion and fuse together. This process of nuclear fusion is what distinguishes a true star from all other objects in the universe, and reaching that critical temperature requires the protostar to accumulate sufficient mass for gravity to compress the core to the necessary extreme. The surrounding disk continues to feed material onto the growing protostar, but this accretion process is neither smooth nor steady. Observations of young stellar objects reveal that they experience periodic outbursts, moments when the rate of material falling onto the protostar suddenly increases dramatically. These events, known as Fu Orionis outbursts after the first star observed to exhibit this behavior, can increase the brightness of a young stellar object by a factor of 100 or more, lasting for decades before gradually subsiding. During these outbursts, the protostar briefly shines with a luminosity that rivals or even exceeds what it will produce as a mature, stable star. The mechanism behind these dramatic events involves instabilities in the accretion disk regions, where material has accumulated faster than it can spiral inward, suddenly release their stored mass in a cascade that floods the protostar with new fuel. These outbursts may play an important role in the final stages of star formation, helping to clear away the remaining envelope of gas and dust that surrounds the young stellar object. As the protostar approaches its final mass, powerful winds begin to blow outward from its poles. These bipolar outflows, driven by magnetic fields threading through the rotating disk, can extend for light years into space, carrying material away from the star-forming region at velocities of hundreds of kilometers per second. The outflows carve channels through the surrounding cloud, creating the distinctive hourglass shapes visible in many images of stellar nurseries. These outflows serve a vital function in the star formation process. Without them, the angular momentum of the infalling material would prevent the protostar from ever achieving the density necessary for nuclear fusion. By carrying away both mass and angular momentum, the bipolar outflows allow the remaining material to continue its inward spiral, feeding the growing protostar until it finally crosses the threshold into true stellar existence. The transition from protostar to star does not happen suddenly or dramatically. There is no single moment when the object transforms from one state to another. Instead, the core temperature rises gradually until, somewhere around 10 million degrees, the first sustained fusion reactions begin. These initial reactions are tentative and sporadic, flickering to life and dying away as the core temperature fluctuates around the critical threshold. But as more material accumulates and the core compression increases, the fusion reactions become more stable, more persistent, until finally they achieve a self-sustaining equilibrium. At this moment, a new star is born. The energy released by nuclear fusion in the core creates an outward pressure that balances the inward pull of gravity, halting the collapse that has been proceeding for millions of years. The star settles into a stable configuration, its size and temperature determined by the total mass it has accumulated during its formation. This balance between gravity and pressure, called hydrostatic equilibrium, will persist for millions or even billions of years as the star slowly converts its hydrogen fuel into helium and radiates energy out into the cosmos. The molecular cloud that gave birth to this new star rarely produces just a single stellar offspring. More commonly, the collapse fragments into multiple cores, each giving rise to its own protostar. These sibling stars form in close proximity to one another, their gravitational influences intertwining in complex ways. Some will remain bound together as binary or multiple star systems, orbiting one another for their entire lives. Others will be flung away by gravitational interactions, becoming solitary wanderers in the galaxy. The most massive molecular clouds can give birth to thousands of stars in a single episode of star formation. These stellar nurseries produce open clusters, loose associations of young stars that share a common origin and move through space together. Famous examples include the Pleiades, visible to the naked eye as a tight grouping of bright blue stars in the constellation Taurus, and the Orion Nebula cluster, hidden within the glowing gas of one of the most photographed objects in the night sky. Over time, these open clusters gradually disperse as their member stars drift apart. The gravitational bonds holding them together are weak compared to the disruptive influences they encounter passing stars, giant molecular clouds, and the tidal forces of the galaxy itself all work to separate the siblings. After a few 100 million years, most open clusters have dissolved entirely, their former members scattered across the galaxy with no obvious connection to their birth companions. Yet traces of these ancient family relationships can still be detected by careful observation. Stars born from the same molecular cloud share similar chemical compositions, fingerprints of their common origin that persist even after billions of years of separation. By analysing the spectra of stars throughout the galaxy, astronomers can identify these chemical signatures and reconstruct the family trees of stellar populations, tracing the history of star formation across cosmic time. The molecular clouds themselves are not permanent features of the galaxy. They form through the accumulation of diffuse interstellar gas, compressed by spiral density waves or the expanding shells of old supernova remnants. They persist for perhaps 10 to 30 million years before being dispersed by the very stars they create. The intense radiation and powerful winds from young massive stars gradually erode the cloud from within, exposing the newly formed stellar cluster to the wider universe. This cycle of cloud formation, star birth, and cloud dispersal continues throughout the galaxy, maintaining a rough equilibrium between the creation and destruction of molecular clouds. The rate of star formation in the Milky Way has varied over cosmic time, peaking billions of years ago when the galaxy was younger and its gas supply more abundant. Today, the Milky Way produces perhaps 1 to 3 solar masses worth of new stars each year, a modest rate compared to the galaxy's youth, but still sufficient to ensure that stellar nurseries remain active throughout the galactic disk. As we contemplate these vast stellar nurseries, drifting through the darkness of interstellar space, we might find a certain peace in their patient processes. There is no urgency in the formation of a star, no deadline that must be met. Gravity simply does what gravity does, pulling matter together with infinite patience, allowing the universe to create new sources of light and warmth on its own unhurried schedule. In a cosmos often characterized by violent events and dramatic transformations, the birth of a star unfolds with a gentleness that belies the enormous energies involved. And so the ancient dance continues, as it has for billions of years and will continue for billions more. Molecular clouds collapse, protostars form, nuclear fires ignite, and new stars take their places in the cosmic tapestry of light. Each star that shines in the night sky began its existence in just this way, emerging from darkness and cold to become a beacon of warmth and illumination. The process is ongoing even now, in countless stellar nurseries scattered throughout our galaxy and beyond, ensuring that the universe will never lack for new stars to light its vast expanses. When nuclear fusion first ignites in the core of a young star, something profound occurs, a transformation so fundamental that it marks the true beginning of stellar life. The protostar, which has spent millions of years gathering material and compressing its core, finally achieves the conditions necessary for hydrogen nuclei to overcome their electrical repulsion and merge together. This process, called nuclear fusion, releases energy in quantities that dwarf any chemical reaction known on Earth, and it is this energy that will sustain the star for millions or billions of years to come. The specific reaction that powers most stars is called the proton-proton chain, and understanding it requires us to venture into the realm of nuclear physics. At the heart of every hydrogen atom lies a single proton, a positively charged particle roughly 1,800 times more massive than an electron. Under normal circumstances, two protons brought close together will repel one another fiercely, their positive charges creating an electrical force that pushes them apart. This repulsion is strong enough that, at room temperature, protons would need to be accelerated to nearly the speed of light to overcome it and collide. But in the core of a star, conditions are anything but normal. The temperature exceeds 10 million degrees, and the pressure reaches values that would crush any material known on Earth into oblivion. Under these extreme conditions, protons move at tremendous velocities, and occasionally, very occasionally, two of them approach close enough for a different force to take over. This is the strong nuclear force, which operates only at extremely short ranges, but is powerful enough to bind protons and neutrons together into atomic nuclei. When two protons fuse, something remarkable happens. One of the protons transforms into a neutron through a process called beta plus decay, releasing a positron and a neutrino in the process. The resulting particle, one proton and one neutron bound together, is called deuterium, or heavy hydrogen. This initial fusion reaction is actually quite rare, even in the extreme conditions of a stellar core. A typical proton in the Sun will wait, on average, about 9 billion years before successfully fusing with another proton. Yet with countless trillions upon trillions of protons in the solar core, enough reactions occur each second to power our star. The deuterium nucleus does not remain alone for long. Within a second or so, it captures another proton, forming helium-3, an isotope of helium containing two protons and one neutron. This reaction releases a gamma-ray photon, a packet of electromagnetic energy that begins a long journey outward from the core. The helium-3 nucleus, in turn, eventually encounters another helium-3 nucleus, and the two fuse to form ordinary helium-4 while releasing two protons back into the stellar plasma. The net result of this chain of reactions is the conversion of 4 hydrogen nuclei into 1 helium nucleus, with the release of energy in the form of gamma rays, positrons, and neutrinos. The energy released comes from a tiny difference in mass between the initial hydrogen and the final helium. The helium nucleus weighs slightly less than the 4 protons that went into making it. This missing mass has been converted directly into energy according to Einstein's famous equation E equals mc squared. The amount of mass converted in each reaction is minuscule less than 1% of the original hydrogen mass. Yet when multiplied by the speed of light squared, this tiny mass difference yields an enormous amount of energy. The Sun converts approximately 4 million tons of matter into pure energy every second, a rate that has persisted for 4.5 billion years and will continue for roughly 5 billion more. This prodigious energy output is what makes stars shine, what warms planets, and what ultimately makes life possible in the universe. The gamma-ray photons produced in the core do not travel directly to the surface. Instead, they begin an incredibly long and tortuous journey outward, constantly being absorbed and re-emitted by the dense stellar plasma. Each absorption and re-emission changes the direction of the photon randomly, creating a path that resembles a drunkard's walk more than a straight line. The distance from the Sun's core to its surface is only about 700,000 kilometers, yet a photon takes, on average, roughly 100,000 years to complete this journey. During this extended migration, the photons gradually lose energy. Each interaction with the stellar plasma tends to produce lower energy photons, so by the time the radiation reaches the surface, the gamma rays have been transformed into visible light, infrared radiation, and other less energetic forms. This is why the Sun appears to shine with yellow-white light rather than the deadly gamma radiation produced in its core. The energy has been processed and diluted during its long journey outward. The neutrinos produced by nuclear fusion follow a very different path. These ghostly particles interact so weakly with ordinary matter that they pass through the entire star in just 2 seconds, escaping into space at nearly the speed of light. Trillions of solar neutrinos pass through your body every second, day and night, yet they almost never interact with the atoms that make up your flesh. Detecting these elusive particles requires enormous underground detectors filled with thousands of tons of water or other materials, waiting patiently for the rare occasions when a neutrino happens to collide with an atom. When astronomers first measured the flux of neutrinos from the Sun in the 1960s, they discovered a puzzle that would take decades to solve. The detected neutrino rate was only about 1/3 of what theoretical models predicted, a discrepancy that became known as the solar neutrino problem. The resolution came from particle physics rather than astrophysics. Neutrinos, it turns out, come in 3 different types, and they can transform from one type to another as they travel through space. The original detectors were sensitive to only one type, missing the neutrinos that had changed flavour during their journey from Sun to Earth. The confirmation that solar neutrinos behave exactly as predicted by our models of stellar fusion provided powerful evidence that we truly understand how stars generate their energy. The nuclear reactions occurring in the Sun's core, hidden from direct observation by hundreds of thousands of kilometres of opaque plasma, are precisely those we have deduced from the principles of physics. This concordance between theory and observation represents one of the great triumphs of 20th century astrophysics. Young stars that have just begun nuclear fusion enter a phase of their lives called the T-Tauri stage, named after the prototype star in the constellation Taurus. T-Tauri stars are characterized by irregular variability in their brightness, powerful stellar winds, and the presence of circumstellar disks left over from their formation. These stars have not yet settled into the stable equilibrium that characterizes mature stars. Their internal structure is still adjusting to the onset of nuclear fusion, and their surfaces are marked by intense magnetic activity. The variability of T Tauri stars arises from several sources. Large star spots, similar to sunspots but covering a much greater fraction of the stellar surface, rotate in and out of view as the star spins, causing periodic brightness changes. Irregular accretion from the surrounding disk adds additional variability as clumps of material falling onto the star release gravitational energy in unpredictable bursts, and powerful flares driven by magnetic reconnection events far more energetic than anything seen on our Sun can temporarily increase the star's brightness by significant factors. The stellar winds from T Tauri stars are remarkably powerful, carrying away mass at rates up to 1 billion times greater than the solar wind. These winds gradually clear away the remaining gas and dust from the star's immediate vicinity, exposing the young star to direct observation for the first time. The process takes several million years, during which the star transitions from an embedded, invisible object to a visible member of its birth cluster. The circumstellar disks around T Tauri stars are of particular interest because they are the sites where planets form. These protoplanetary disks, as they are called, contain all the raw materials necessary for building worlds: hydrogen and helium gas, water ice, silicate rocks, and metals forged in the hearts of previous generations of stars. Within these disks, dust grains collide and stick together, gradually building larger and larger objects until planetesimals, asteroids, and eventually planets emerge. The study of protoplanetary disks has been revolutionized in recent years by the Atacama Large Millimeter Array, a collection of radio telescopes in the Chilean desert capable of imaging these disks in unprecedented detail. The images reveal intricate structures, rings, gaps, and spiral arms that suggest planets are already forming within these young systems. Some disks show clear evidence of protoplanets carving out gaps in the disk material, their gravitational influence creating visible signatures in the surrounding gas and dust. The T Tauri phase typically lasts for roughly 10 million years, during which the star gradually settles into a more stable configuration. The irregular variability diminishes as the magnetic activity calms. The stellar wind weakens as the star's rotation slows, and the circumstellar disk either forms planets or is dispersed by radiation and winds. By the end of this phase, the young star has become a mature main sequence object, ready to spend the bulk of its existence steadily converting hydrogen into helium. Not all young stars follow this standard path, however. The most massive stars, those with more than about 8 times the mass of our Sun, evolve so rapidly that they skip the T Tauri phase entirely. These stellar giants reach the main sequence while still embedded within their birth clouds, their intense radiation and powerful winds quickly dispersing the surrounding material. The entire process of formation and early evolution, which takes tens of millions of years for a Sun-like star, is compressed into less than 100,000 years for the most massive stars. At the other end of the mass spectrum, the smallest stars take far longer to reach maturity. Red dwarfs with their masses less than half that of the Sun may spend 100 million years or more in their pre-main sequence phase, gradually contracting and heating until fusion finally ignites in their cores. These diminutive stars are so numerous that they dominate the stellar population of the galaxy, yet their faintness makes them difficult to study. Only in recent decades have astronomers begun to appreciate the full diversity of these cool, dim objects. The transition from pre-main sequence to main sequence is marked by the establishment of a stable equilibrium between gravity and pressure. The star stops contracting, its core temperature stabilizes at whatever value is necessary to generate enough energy to support the overlying layers, and the surface settles into a consistent temperature and luminosity. This equilibrium will persist for as long as hydrogen fuel remains in the core span that ranges from a few million years for the most massive stars to trillions of years for the smallest red dwarfs. As a star settles onto the main sequence, it takes its place on one of the most important diagrams in all of astronomy, the Hertzsprung-Russell diagram, which plots stellar luminosity against surface temperature. This diagram, developed independently by Einar Hertzsprung and Henry Norris Russell in the early 20th century, reveals the fundamental relationships between stellar properties and provides a framework for understanding stellar evolution. The main sequence appears as a diagonal band running from hot, luminous blue stars in the upper left to cool, dim red stars in the lower right. The position of a star on the main sequence is determined almost entirely by its mass. More massive stars have higher core temperatures, faster fusion rates, and greater luminosities. They also have higher surface temperatures, giving them blue or blue-white colours. Less massive stars have lower core temperatures, slower fusion rates, and lower luminosities. Their surfaces are cooler, producing yellow, orange, or red colours. This relationship between mass and position on the main sequence is so tight that astronomers can estimate a star's mass simply by measuring its colour and brightness. The main sequence is not a single line, but rather a band with some width, reflecting the fact that stars of similar mass can have slightly different compositions or ages. Stars that have been fusing hydrogen for longer have accumulated more helium in their cores, slightly altering their structure and position on the diagram. Stars with higher concentrations of heavy elements inherited from the gas clouds that formed them also show subtle differences in their properties. These variations provide clues to stellar ages and origins that astronomers can exploit to reconstruct the history of star formation in the galaxy. As we contemplate the birth of stars and their emergence onto the main sequence, we witness one of nature's most remarkable transformations. From cold, diffuse clouds of gas and dust, gravity sculpts objects of incredible density and temperature, objects capable of sustaining nuclear fusion for billions of years. The light that reaches our eyes from even the nearest stars began as gamma radiation in stellar cores, processed and transformed during journeys lasting thousands of centuries. And the neutrinos streaming through our bodies at this very moment carry direct information about nuclear reactions occurring right now, 150 million kilometers away in the heart of our own star. The universe creates stars with a patience and persistence that dwarfs any human endeavour. The processes involved span millions of years and light years of space, yet they operate according to the same physical laws we discover in our laboratories on Earth. This continuity between the cosmic and the terrestrial, between the birth of stars in distant nebulae and the physics we study in our universities, represents one of the most profound insights of modern science. We are not separate from the cosmos, we are part of it, made of atoms forged in stellar cores, contemplating the very processes that gave rise to our existence. When a star completes its formation and settles into the stable burning of hydrogen in its core, it enters the longest and most peaceful phase of its existence. This is the main sequence, a term that refers both to a stage of stellar evolution and to the prominent band of stars that dominates the Hertzsprung-Russell diagram. A star will spend roughly 90% of its total lifetime on the main sequence, steadily converting hydrogen into helium while maintaining a delicate balance between the crushing force of gravity and the outward pressure generated by nuclear fusion. The Hertzsprung-Russell diagram, often abbreviated as the HR diagram, stands as one of the most powerful tools in stellar astronomy. Developed in the early 20th century, this seemingly simple plot of stellar luminosity versus surface temperature reveals the fundamental relationships that govern stellar structure and evolution. When astronomers first plotted large numbers of stars on this diagram, they discovered that stars do not occupy random positions. Instead, they cluster in specific regions that correspond to different evolutionary stages. The main sequence dominates the HR diagram, running diagonally from the upper left, where hot, luminous blue stars reside, to the lower right, where cool, dim red stars gather. This band contains the vast majority of all stars in the galaxy, reflecting the fact that hydrogen burning is the longest-lasting phase of stellar evolution. Stars enter the main sequence from above, descending from the pre-main sequence region as they complete their formation. They leave the main sequence by moving to the right, expanding and cooling as they exhaust their core hydrogen and begin the next phase of their evolution. The position of a star on the main sequence is determined primarily by a single property, its mass. This relationship between mass and position is so fundamental that astronomers speak of the mass-luminosity relation, a tight correlation that allows stellar masses to be estimated from brightness measurements alone. The physics behind this relation is straightforward. More massive stars have stronger gravitational compression, which produces higher core temperatures, faster fusion rates, and greater energy output. The relationship is not linear. A star with twice the mass of the Sun produces roughly 16 times as much light, not twice as much. This mass-luminosity relation has profound implications for stellar lifetimes. More massive stars burn through their hydrogen fuel far more rapidly than their less massive counterparts, despite having more fuel to begin with. A star with 10 times the mass of the Sun has perhaps 10 times as much hydrogen available for fusion, but it consumes this fuel at roughly 10,000 times the rate. The result is a lifetime measured in tens of millions of years rather than billions. The most massive stars known, with masses exceeding 100 times that of the Sun, live for only a few million years, barely enough time for light to travel from one end of a typical galaxy to the other. At the opposite extreme, the smallest main sequence stars hoard their fuel with extraordinary efficiency. Red dwarfs, with masses around 1/10 that of the Sun, produce so little energy that their hydrogen supplies will last for trillions of years, far longer than the current age of the universe. No red dwarf that has ever formed has yet had time to exhaust its hydrogen fuel. These diminutive stars will continue shining long after the last massive blue giants have exploded and faded, serving as the final stellar inhabitants of an aging cosmos. Astronomers classify main sequence stars according to their surface temperatures using a system of spectral types. The classification scheme uses the letters O, B, A, F, G, K, and M, running from hottest to coolest. This seemingly random sequence of letters is a historical artifact. The original classification was based on the strength of hydrogen absorption lines in stellar spectra, and the letters were rearranged when astronomers realized that temperature, not hydrogen abundance, was the underlying variable. O-type stars are the hottest and most luminous, with surface temperatures exceeding 30,000 degrees, and luminosities that can reach 1 million times that of the Sun. These stellar giants appear blue-white to the eye and emit most of their radiation in the ultraviolet part of the spectrum. They are exceedingly rare, comprising less than 1 in 3 million stars in the galaxy, yet their extreme luminosity makes them visible across vast distances. The bright stars that outline the constellation Orion includes several O-type stars, their blue-white light dominating the winter sky. B-type stars are slightly cooler, with temperatures between 10,000 and 30,000 degrees. They appear blue or blue-white and include many of the brightest stars visible to the naked eye. Rigel, the brightest star in Orion, is a B-type supergiant, while the stars of the Pleiades cluster are B-type main sequence objects. Like O-type stars, B-type stars are relatively rare and short-lived, but their brilliance makes them prominent features of the night sky. A-type stars have surface temperatures between 7,500 and 10,000 degrees, giving them white or blue-white colours. Sirius, the brightest star in the night sky, is an A-type main sequence star, as is Vega, one of the vertices of the summer triangle. These stars are more common than O and B types, but still represent only a small fraction of the total stellar population. F-type stars with temperatures between 6,000 and 7,500 degrees appear white or yellow-white. These stars are similar to our Sun in many respects, though somewhat hotter and more luminous. Procyon, visible in the winter sky as part of the winter triangle, is an F-type star nearing the end of its main sequence lifetime. G-type stars include our own Sun, with surface temperatures between 5,200 and 6,000 degrees. These yellow stars are often considered ideal for hosting habitable planets, as their moderate temperatures and long lifetimes provide stable conditions for billions of years. Alpha Centauri A, the larger component of the nearest stellar system to our own, is also a G-type star, remarkably similar to the Sun in size, temperature, and luminosity. K-type stars are cooler still, with temperatures between 3,700 and 5,200 degrees. These orange stars are more numerous than all the hotter spectral types combined, and include many well-known objects, such as Alpha Centauri b and Epsilon Eridani. Their lower luminosities mean that any habitable planets would need to orbit quite close to the star, but their long lifetimes exceeding 15 billion years for the coolest K-types provide ample time for complex life to develop. M-type stars, the red dwarfs, are by far the most numerous stellar type in the galaxy. With surface temperatures below 3,700 degrees, these cool dim stars emit most of their radiation in the infrared, making them difficult to observe despite their abundance. Proxima Centauri, the nearest star to our Sun, is an M-type red dwarf, as is Barnard's star, the second nearest stellar system. Estimates suggest that red dwarfs comprise roughly 70% of all stars in the Milky Way, yet not a single one is visible to the naked eye from Earth. Each spectral type is further subdivided using numbers from 0 to 9, with 0 representing the hottest stars within each class and 9 the coolest. Our Sun, for instance, is classified as a G2 star, placing it toward the hotter end of the G-type range. This numerical subdivision allows astronomers to specify stellar temperatures with considerable precision, enabling detailed comparisons between stars and accurate predictions of their physical properties. Beyond the main spectral classification, astronomers also assign luminosity classes that indicate whether a star is a main sequence object, a giant, or a supergiant. Main sequence stars receive the Roman numeral 5 in this system, so our Sun's complete classification is G2VA G-type star, subdivision 2, on the main sequence. This compact notation encodes a wealth of information about the star's temperature, luminosity, size, and evolutionary state, allowing astronomers to communicate stellar properties efficiently. The physical conditions within a main sequence star vary enormously from core to surface. At the centre, where nuclear fusion occurs, temperatures reach millions of degrees, and densities exceed that of solid lead. The pressure at the Sun's core is roughly 250 billion times the atmospheric pressure at Earth's surface conditions, so extreme that they cannot be replicated in any laboratory on our planet. Yet these conditions are necessary for fusion to proceed, for only at such temperatures and pressures can hydrogen nuclei approach closely enough for the strong nuclear force to bind them together. Moving outward from the core, temperature and density decrease steadily. The region immediately surrounding the core, called the radiative zone, transports energy outward through the absorption and re-emission of photons. This process is extraordinarily slow, as each photon travels only a short distance before being absorbed by an atom, which then re-emits the energy in a random direction. The journey of a photon through the radiative zone follows a random walk that takes, on average, roughly 170,000 years to complete in a star like our Sun. Above the radiative zone lies the convective zone, where energy transport occurs through the physical motion of hot gas. In this region, hot plasma rises toward the surface, releases its energy, cools and sinks back down to be reheated. This convective churning creates the granular pattern visible on the Sun's surface, a constantly shifting mosaic of bright cells surrounded by darker boundaries, each cell representing the top of a rising column of hot gas. The individual granules are roughly 1,000 kilometers across and last for only about 10 minutes before being replaced by new convective cells. The relative sizes of the radiative and convective zones depend strongly on stellar mass. In the Sun, the radiative zone extends from the core to about 70% of the solar radius, with the convective zone occupying the outer 30%. More massive stars have larger radiative zones and smaller convective zones, while less massive stars show the opposite pattern. The smallest red dwarfs are fully convective, with no radiative zone at all. Hot gas circulates from the core all the way to the surface, thoroughly mixing the stellar interior. This difference in internal structure has important consequences for stellar evolution. In stars with radiative cores, the products of nuclear fusion, primarily helium, accumulate at the centre, unable to mix with the hydrogen-rich envelope above. Over time, this creates a helium-rich core surrounded by a hydrogen-rich shell, a configuration that eventually leads to dramatic changes in stellar structure. In fully convective stars, by contrast, the fusion products are continuously mixed throughout the star, allowing these objects to burn a much larger fraction of their total hydrogen supply. The surface of a main sequence star, called the photosphere, is the layer from which most of the star's light escapes into space. Despite being the visible face of the star, the photosphere is actually quite thin, only a few hundred kilometers deep in a star like the Sun. The temperature of the photosphere determines the star's color, with hotter photospheres producing blue light and cooler ones producing red. The Sun's photosphere has a temperature of approximately 5,500 degrees Celsius, giving it the yellow-white color we observe. Above the photosphere lies the chromosphere, a thin layer of hotter, more tenuous gas that is normally invisible against the brilliant photosphere below. The chromosphere can be observed during total solar eclipses, when the moon blocks the photosphere and reveals a thin pinkish ring around the darkened disk. The pink color comes from hydrogen atoms emitting light at a specific wavelength called hydrogen alpha, a characteristic emission that allows astronomers to image the chromosphere using specialized filters. Beyond the chromosphere extends the corona, the outermost layer of the stellar atmosphere. The corona presents one of the great puzzles of solar physics, for its temperature exceeds 1 million degrees far hotter than the photosphere below. This temperature inversion seems to violate basic thermodynamics, which suggests that heat should flow from hot regions to cold, not the reverse. The solution to this puzzle involves magnetic fields and the complex plasma physics of the outer atmosphere, though the details remain an active area of research. The corona is visible during total solar eclipses as a pearly white halo extending millions of kilometers from the solar surface. Its extreme temperature causes it to emit primarily in X-rays and extreme ultraviolet light, wavelengths that are absorbed by Earth's atmosphere and thus invisible from the ground. Space-based observatories have revolutionized our understanding of the corona, revealing a dynamic environment shaped by magnetic fields, heated by wave dissipation and magnetic reconnection, and constantly streaming outward as the solar wind. Main sequence stars are not perfectly static objects. They pulsate, rotate, flare, and vary in brightness on timescales ranging from minutes to decades. The Sun, despite its apparent constancy, actually varies in luminosity by about 0.1% over its 11-year activity cycle. This variation, though small, is sufficient to influence Earth's climate in subtle ways, contributing to historical episodes such as the Little Ice Age that gripped Europe during the 17th century. The 11-year solar cycle reflects the periodic reversal of the Sun's magnetic field, driven by the interaction between rotation and convection in the outer layers. At solar maximum, the Sun's surface is dotted with sunspots, regions of intense magnetic field that appear dark because they are cooler than their surroundings. Solar flares and coronal mass ejections are more frequent during solar maximum, occasionally disrupting communications and power systems on Earth. At solar minimum, the Sun's surface is relatively placid, with few sunspots and reduced activity. Other main sequence stars show similar activity cycles, though the periods and amplitudes vary widely. Some stars appear to have cycles lasting only a few years, while others show no obvious periodicity at all. The level of activity generally correlates with rotation rate. Faster spinning stars tend to be more active, with larger spots, more frequent flares, and stronger magnetic fields. Young stars, which rotate more rapidly than older ones, are typically much more active than their elderly counterparts. Stellar rotation itself varies considerably among main sequence stars. Young stars spin rapidly, completing a rotation in just a day or two, while older stars like the Sun rotate much more slowly, taking about 25 days to complete a single turn. This slowing occurs because the stellar wind carries away angular momentum, gradually breaking the star's rotation over billions of years. The relationship between rotation and age is tight enough that astronomers can estimate stellar ages from rotation periods alone, a technique called gyrochronology. The magnetic fields of main sequence stars are generated by a process called the dynamo mechanism, which converts the kinetic energy of convective motions and rotation into magnetic energy. The details of this process are complex and not fully understood, but the basic principle involves the stretching and twisting of magnetic field lines by the moving plasma. The resulting magnetic field is not uniform, but instead concentrated into tubes and loops that thread through the stellar interior and extend into the corona. These magnetic structures are responsible for much of the activity observed on stellar surfaces. Sunspots form where magnetic flux tubes emerge through the photosphere, inhibiting convection and creating cooler, darker regions. Solar flares occur when magnetic field lines reconnect, releasing stored energy in violent bursts of radiation and accelerated particles. Coronal mass ejections happen when magnetic structures become unstable and erupt outward, carrying billions of tons of plasma into interplanetary space. The solar wind, a continuous outflow of charged particles from the corona, fills the entire solar system with a tenuous plasma. This wind flows outward at speeds ranging from 300 to 800 kilometers per second, carrying the sun's magnetic field with it and creating a vast bubble called the heliosphere. The heliosphere extends far beyond the orbit of Pluto, reaching roughly 120 astronomical units from the Sun before giving way to the interstellar medium. The boundary of the heliosphere, called the heliopause, marks the edge of the Sun's direct influence on its environment. Beyond this boundary lies interstellar space, filled with gas and dust from other stars, and the general interstellar medium. The Voyager spacecraft, launched in 1977, crossed the heliopause in 2012 and 2018, becoming the first human-made objects to enter interstellar space. Their instruments continue to return data about conditions in this unexplored realm, revealing a complex environment shaped by the interaction between the solar wind and the surrounding galaxy. Every main sequence star creates its own equivalent of the heliosphere, a bubble of stellar wind that pushes back against the interstellar medium. The size and shape of these bubbles depend on the strength of the stellar wind and the density of the surrounding gas. Massive stars with powerful winds create enormous bubbles that can span dozens of light years, while red dwarfs with weak winds produce much smaller structures. These stellar wind bubbles play an important role in shaping the interstellar medium, creating cavities and shells that influence subsequent generations of star formation. The stability of main sequence stars makes them ideal hosts for planetary systems. The steady energy output provides consistent conditions for billions of years, allowing complex chemistry to develop on planetary surfaces and potentially life to evolve. Our own existence is intimately tied to the Sun's main sequence stability. The 4.5 billion years since Earth's formation have seen remarkably little variation in solar luminosity, providing the stable environment necessary for life to emerge and diversify. Yet this stability is not eternal. Every main sequence star is slowly consuming its hydrogen fuel, gradually altering its internal structure in ways that will eventually lead to dramatic changes. The Sun, for instance, has grown roughly 30% more luminous since its formation, a slow brightening that will continue until the hydrogen in the core is finally exhausted. This gradual evolution is imperceptible on human timescales, but profound over geological time, influencing planetary climates and potentially rendering once habitable worlds uninhabitable. The main sequence, then, is not a static destination, but rather a long, slow journey. Stars enter this phase as newly formed objects, fresh from their natal clouds, and leave it billions of years later as evolved giants or supergiants. The time spent on the main sequence represents the prime of stellar life, a period of stability and steady energy production that enables the complex phenomena we observe throughout the universe. Without main sequence stars, there would be no planets, no life, no astronomers to contemplate the cosmos. The main sequence is where stars do their most important work, shining steadily across the ages and making the universe a habitable place. Deep within every star lies a realm of almost unimaginable extremity, where temperatures soar to millions of degrees and pressures crush matter into states unknown on Earth. This is the stellar core, the engine that powers the star's luminosity and determines its ultimate fate. Understanding the physics of stellar cores requires us to venture into the quantum realm, where particles behave in ways that defy everyday intuition and where the fundamental forces of nature compete for dominance. The core of a main sequence star is a nuclear furnace, converting hydrogen into helium through processes that release enormous quantities of energy. The specific reactions that accomplish this transformation depend on the star's mass and core temperature, with different pathways dominating in different stellar environments. In stars like our Sun, the proton-proton chain provides most of the energy, while in more massive stars, a different sequence called the carbon-nitrogen-oxygen cycle takes precedence. The proton-proton chain, which we encountered earlier, proceeds through several steps that gradually build helium nuclei from individual protons. The first and slowest step involves the fusion of two protons to form deuterium, a reaction that requires one proton to transform into a neutron through the weak nuclear force. This transformation is exceedingly rare. The weak force is aptly named, being roughly 1,000,000 times weaker than the electromagnetic force that normally governs atomic interactions. A typical proton in the solar core will collide with other protons countless trillions of times before finally undergoing this transformation. The rarity of this initial reaction is actually crucial for the Sun's longevity. If proton-proton fusion occurred more readily, the Sun would burn through its hydrogen fuel far more rapidly, exhausting its supply in mere millions of years rather than billions. The weakness of the weak force acts as a throttle on the fusion rate, allowing the Sun to shine steadily for the roughly 10 billion years necessary for complex life to evolve on Earth. In a very real sense, we owe our existence to the feebleness of the weak nuclear force. Once deuterium forms, the subsequent reactions proceed much more rapidly. Deuterium captures another proton within about a second, forming helium-3 and releasing a gamma-ray photon. Two helium-3 nuclei then combine to form helium-4, releasing two protons in the process. The net result is the conversion of 4 protons into one helium-4 nucleus, 2 positrons, 2 neutrinos, and several gamma-ray photons. The mass of the final products is slightly less than the mass of the initial protons, with the difference appearing as the kinetic energy of the products and the energy of the photons. The energy released in each complete cycle of the proton-proton chain amounts to roughly 26 million electron volts. A tiny quantity by everyday standards, but enormous compared to chemical reactions. For comparison, the combustion of a single carbon atom releases only about 4 electron volts, roughly 6 million times less energy than hydrogen fusion. This vast difference explains why nuclear reactions can power stars for billions of years while chemical reactions cannot. In stars more massive than about 1 1/3 times the mass of the Sun, core temperatures exceed roughly 15 million degrees, and a different fusion pathway becomes dominant. This is the carbon-nitrogen-oxygen cycle, often abbreviated as the CNO cycle, which uses carbon, nitrogen, and oxygen nuclei as catalysts to facilitate hydrogen fusion. The CNO cycle does not consume these heavier elements. They are recycled through the reaction sequence, emerging unchanged at the end while having enabled the conversion of hydrogen to helium. The CNO cycle begins when a carbon-12 nucleus captures a proton, forming nitrogen-13 and releasing a gamma-ray. The nitrogen-13 is unstable and quickly decays to carbon-13, emitting a positron and a neutrino. Carbon-13 then captures another proton, forming nitrogen-14 and releasing another gamma-ray. Nitrogen-14 captures a proton to form oxygen-15, which decays to nitrogen-15 with the emission of a positron and neutrino. Finally, nitrogen-15 captures a proton and splits into carbon-12 and helium-4, returning the carbon catalyst to its original form and completing the cycle. The net result of the CNO cycle is identical to that of the proton-proton chain. 4 protons are converted into one helium nucleus with the release of 2 positrons, 2 neutrinos, and gamma-ray photons. The energy yield is also similar, around 25 million electron volts per cycle. The The key difference lies in the temperature sensitivity of the two pathways. The proton-proton chain rate increases relatively slowly with temperature, roughly as the fourth power. The CNO cycle rate, by contrast, increases as roughly the 16th power of temperature, making it extraordinarily sensitive to core conditions. This extreme temperature sensitivity means that the CNO cycle dominates in massive stars with their hotter cores, while the proton-proton chain dominates in lower mass stars like the Sun. The transition between the two regimes occurs around 1 1/3 solar masses, where both pathways contribute roughly equally to the total energy production. Above this mass, the CNO cycle rapidly takes over, producing the vast majority of the star's energy output. The dominance of the CNO cycle in massive stars has important consequences for stellar structure. Because the cycle is so temperature sensitive, even small changes in core temperature produce large changes in energy output. This creates a situation where the core temperature remains nearly constant regardless of the star's luminosity. Any increase in temperature would dramatically boost the energy production, causing the core to expand and cool back down. The result is that massive stars have cores of nearly uniform temperature, with energy production concentrated in a small central region. The energy generated in stellar cores must somehow escape to the surface, a journey that involves two distinct transport mechanisms. In the radiative zone, energy moves outward through the absorption and re-emission of photons. Each photon travels only a short distance, roughly a centimetre, in the solar interior before being absorbed by an atom or ion. The absorbing particle then re-emits the energy as a new photon, which travels in a random direction before being absorbed again. This random walk process is extraordinarily inefficient, requiring hundreds of thousands of years for energy to traverse the radiative zone. During this long journey, the photons gradually lose energy through each interaction. The gamma rays produced in nuclear reactions are progressively degraded into X-rays, then ultraviolet light, and finally visible and infrared radiation. By the time the energy reaches the stellar surface, it has been diluted and transformed almost beyond recognition. The deadly gamma radiation of the core emerges as the gentle warmth of sunlight, processed and softened by countless interactions with the stellar plasma. In the convective zone, energy transport occurs through the physical motion of hot gas rather than the diffusion of photons. Hot plasma rises toward the surface, carrying its thermal energy with it. Upon reaching the top of the convective zone, the plasma radiates its energy into space, cools, and sinks back down to be reheated. This convective circulation is far more efficient than radiative transport, moving energy outward at speeds of several kilometers per second rather than the glacial pace of photon diffusion. The boundary between the radiative and convective zones is not arbitrary, but is determined by the local conditions within the star. Convection occurs when the temperature gradient, the rate at which temperature decreases with distance from the core, exceeds a critical value called the adiabatic gradient. When this condition is met, rising parcels of gas remain buoyant as they expand and cool, allowing convection to proceed. When the temperature gradient is less steep, rising gas cools faster than its surroundings and sinks back down, suppressing convection. In the Sun, the transition between radiative and convective zones occurs at about 70% of the solar radius. Below this boundary, the temperature gradient is gentle enough that radiative transport suffices. Above it, the increasing opacity of the cooler plasma creates a steeper temperature gradient that triggers convection. The location of this boundary varies with stellar mass. More massive stars have larger radiative zones, while less massive stars have larger convective zones. The smallest red dwarfs are fully convective, with no radiative zone at all. The fully convective nature of red dwarfs has profound implications for their evolution. In stars with radiative cores, the helium produced by fusion accumulates at the center, unable to mix with the hydrogen-rich envelope above. This creates a helium-rich core that gradually grows as fusion proceeds, eventually triggering dramatic changes in stellar structure. In fully convective stars, by contrast, the fusion products are continuously mixed throughout the star, preventing the formation of a distinct helium core. This mixing allows red dwarfs to burn a much larger fraction of their total hydrogen supply than stars like the Sun. While the Sun will exhaust only the hydrogen in its core, roughly 10% of its total mass, before leaving the main sequence, a fully convective red dwarf can potentially burn most of its hydrogen before running out of fuel. Combined with their low fusion rates, this efficient fuel usage gives red dwarfs lifetimes measured in trillions of years, far exceeding the current age of the universe. The neutrinos produced by nuclear fusion provide a unique window into stellar cores. Unlike photons, which take hundreds of thousands of years to escape from the solar interior, neutrinos pass through the entire star in just 2 seconds, carrying direct information about conditions at the center. Detecting these ghostly particles requires enormous underground detectors, shielded from cosmic rays and other background radiation that would otherwise overwhelm the faint neutrino signal. The first solar neutrino detectors, built in the 1960s, use large tanks of cleaning fluid deep underground. Neutrinos occasionally interact with chlorine atoms in the fluid, converting them to radioactive argon that can be extracted and counted. The results of these early experiments revealed a puzzling discrepancy. The detected neutrino rate was only about 1/3 of what theoretical models predicted. This solar neutrino problem persisted for decades, resisting explanation by any modification of stellar models. The resolution came not from astrophysics, but from particle physics. Neutrinos, it turns out, come in 3 different types or flavors: electron neutrinos, muon neutrinos, and tau neutrinos. The fusion reactions in the Sun produce only electron neutrinos, but these particles can transform into other flavors as they travel through space, a phenomenon called neutrino oscillation. The early detectors were sensitive only to electron neutrinos, missing those that had changed flavor during their journey from Sun to Earth. Modern neutrino detectors can measure all 3 flavors, and their results confirm that the total neutrino flux from the Sun matches theoretical predictions almost exactly. This agreement provides powerful evidence that our understanding of stellar nuclear physics is fundamentally correct. The reactions occurring in the solar core, hidden from direct observation by hundreds of thousands of kilometers of opaque plasma, are precisely those we have deduced from the principles of physics. The study of stellar cores extends beyond our own Sun to encompass stars throughout the galaxy and beyond. Astroseismology, the study of stellar oscillations, allows astronomers to probe the internal structure of distant stars much as seismology reveals the interior of Earth. Stars vibrate in complex patterns, with waves travelling through their interiors and causing subtle variations in brightness and velocity. By analysing these oscillations, astronomers can determine the size of stellar cores, the location of boundaries between radiative and convective zones, and even the rotation rates of stellar interiors. The Kepler Space Telescope, launched in 2009 to search for exoplanets, revolutionized astroseismology by providing continuous, high-precision brightness measurements for thousands of stars. These observations revealed stellar oscillations with unprecedented clarity, enabling detailed studies of stellar interiors across a wide range of masses and evolutionary states. The results have confirmed many predictions of stellar structure theory, while also revealing unexpected features that challenge our understanding. One surprising discovery from asteroseismology is that the cores of many red giant stars rotate much more slowly than theoretical models predicted. As stars evolve off the main sequence and their cores contract, conservation of angular momentum should cause the cores to spin faster, much like a figure skater spinning faster as they draw in their arms. Yet observations show that red giant cores rotate only slightly faster than their surfaces, indicating that some mechanism is transferring angular momentum from core to envelope. The nature of this angular momentum transport remains uncertain, though magnetic fields and internal gravity waves are leading candidates. This ongoing puzzle illustrates that stellar physics, despite its long history and many successes, still holds surprises for those who study it carefully. The interiors of stars, hidden from direct view, continue to reveal new phenomena that challenge and refine our understanding of the physical processes that govern stellar evolution. As we contemplate the nuclear furnaces at the hearts of stars, we encounter physics at its most extreme and most fundamental. The reactions that power the sun involve the same forces that govern the behavior of atoms in our laboratories, yet they occur under conditions that we cannot replicate on Earth. The temperatures and pressures of stellar cores represent the ultimate test of our physical theories, and the agreement between prediction and observation confirms that we truly understand the processes that make stars shine. This understanding carries profound implications for our place in the cosmos. The energy that warms our planet, that drives our weather and sustains our biosphere, originates in nuclear reactions occurring 150 million kilometers away, in a realm of unimaginable heat and pressure. The light that reaches our eyes began as gamma radiation in the solar core, transformed by countless interactions during a journey lasting hundreds of millennia, and the neutrinos streaming through our bodies at this very moment carry direct testimony of nuclear fires burning right now, at this very instant, in the heart of our star. Among the hundreds of billions of stars in our galaxy, one holds special significance for us, the Sun, our own star, the source of virtually all energy on Earth, and the gravitational anchor of our planetary system. The Sun is a thoroughly ordinary star by cosmic standards, a middle-aged yellow dwarf of average size and luminosity, yet its proximity to Earth, just 150 million kilometers away, makes it by far the best-studied star in the universe, revealing details of stellar physics that would be invisible in more distant objects. The Sun formed approximately 4.6 billion years ago from a cloud of gas and dust in a spiral arm of the Milky Way galaxy. The same cloud gave rise to the planets, moons, asteroids, and comets that comprise our solar system, all condensing from the rotating disk of material that surrounded the young Sun. The composition of the Sun reflects the chemical makeup of this primordial cloud, roughly 73% hydrogen, 25% helium, and 2% heavier elements forged in previous generations of stars. With a diameter of roughly 1.4 million kilometers, the Sun is large enough to contain more than 1 million Earths. Its mass, approximately 2 × 10 to the 30th kilograms, comprises more than 99% of all matter in the solar system. The planets, for all their diversity and fascination, are mere specks compared to the star they orbit. Jupiter, the largest planet, contains only about 1,000th of the Sun's mass, while Earth is smaller still by a factor of more than 300. The Sun's surface, the photosphere, presents a mottled appearance when viewed through appropriate filters. The granulation pattern, visible in high-resolution images, reveals the tops of convective cells rising from the interior. Each granule is roughly 1,000 kilometers across, about the size of a large country on Earth, and lasts for only about 10 minutes before being replaced by new cells. The pattern constantly shifts and changes, a visible manifestation of the churning convection that transports energy through the outer third of the solar interior. Sunspots are perhaps the most familiar features of the solar surface, dark blemishes that have been observed since ancient times. These regions appear dark because they are cooler than their surroundings, roughly 4,000 degrees compared to the 5,500 degrees of the normal photosphere. The temperature difference arises because strong magnetic fields in sunspots inhibit convection, reducing the flow of heat from below and allowing the surface to cool. Sunspots typically appear in pairs or groups, with opposite magnetic polarities in the two members of each pair. They form when magnetic flux tubes rise through the solar interior and emerge through the photosphere, creating regions of intense magnetic field that suppress the normal convective motions. Individual sunspots can persist for days to weeks, growing, splitting, and eventually dissipating as the magnetic structures that create them evolve and decay. The number of sunspots varies over an approximately 11-year cycle, rising from a minimum of near zero to a maximum of over 100 before declining again. This solar cycle reflects the periodic reversal of the Sun's global magnetic field, driven by the interaction between rotation and convection in the outer layers. At solar maximum, the field is complex and chaotic, with many active regions producing sunspots, flares, and other phenomena. At solar minimum, the field is simpler and more dipolar, with reduced activity across the solar surface. Solar flares are sudden, intense releases of energy that occur in the vicinity of sunspots and other magnetically active regions. These events happen when magnetic field lines become twisted and stressed, storing energy like a wound spring. When the field configuration becomes unstable, the stored energy is released in a matter of minutes, heating plasma to tens of millions of degrees and accelerating particles to near the speed of light. The radiation from a large solar flare spans the entire electromagnetic spectrum, from radio waves to gamma rays. The most energetic flares can release as much energy as 1 billion hydrogen bombs, though this enormous output is still only a tiny fraction of the Sun's total luminosity. The radiation reaches Earth in about 8 minutes, travelling at the speed of light, while the accelerated particles take somewhat longer, arriving over a period of hours to days depending on their energy. Coronal mass ejections are even more dramatic events, involving the expulsion of billions of tons of plasma from the solar corona. These eruptions occur when magnetic structures in the corona become unstable and burst outward, carrying their embedded plasma with them. A typical coronal mass ejection travels outward at speeds of several hundred to several thousand kilometers per second, reaching Earth in 1 to 4 days, depending on its velocity. When a coronal mass ejection strikes Earth's magnetic field, it can trigger geomagnetic storms that affect technology and create beautiful auroral displays. The most severe storms can damage satellites, disrupt radio communications, and even induce currents in power lines that can damage transformers and cause blackouts. The Carrington event of 1859, the most powerful geomagnetic storm in recorded history, induced currents strong enough to shock telegraph operators and set fire to telegraph paper. A similar event today could cause trillions of dollars in damage to our technology-dependent civilization. The solar wind, a continuous outflow of charged particles from the corona, fills interplanetary space with a tenuous plasma. This wind flows outward at speeds of 300 to 800 kilometers per second, carrying roughly 1 million tons of material away from the Sun each second. Despite this prodigious mass loss, the Sun has shed only about 0.1% of its mass to the solar wind over its entire lifetime. The loss is negligible compared to the mass consumed by nuclear fusion. The solar wind creates a vast bubble called the heliosphere, which extends far beyond the orbit of Pluto. Within this bubble, the solar wind dominates the local environment, sweeping away interstellar gas and carrying the sun's magnetic field throughout the solar system. The boundary of the heliosphere, the heliopause, lies roughly 120 astronomical units from the sun, where the pressure of the solar wind finally balances the pressure of the interstellar medium. The sun's influence extends even beyond the heliosphere through its gravitational field. The Oort cloud, a vast spherical shell of icy bodies surrounding the solar system, extends perhaps 100,000 astronomical units from the sun, roughly 1/4 of the distance to the nearest star. Objects in the Oort cloud are so loosely bound to the sun that passing stars can perturb their orbits, occasionally sending comets plunging into the inner solar system on journeys lasting millions of years. The sun is currently in the middle of its main sequence lifetime, having spent roughly 4.5 billion years converting hydrogen to helium in its core. Over this time, the core has gradually accumulated helium ash, slightly contracting and heating as the hydrogen fraction decreases. This slow evolution has caused the sun to brighten by roughly 30% since its formation, a change that has had significant effects on planetary climates. Early in solar system history, the fainter young sun should have been unable to keep Earth's oceans from freezing, a puzzle known as the faint young sun paradox. Yet geological evidence clearly shows that liquid water existed on Earth's surface from very early times, suggesting that some warming mechanism compensated for the reduced solar luminosity. The most likely explanation involves higher concentrations of greenhouse gases in the early atmosphere, though the details remain a subject of active research. Looking forward, the sun will continue to brighten as it ages, with significant consequences for Earth's habitability. In roughly 1 billion years, the increased luminosity will raise global temperatures enough to trigger a runaway greenhouse effect, boiling away the oceans and transforming Earth into a Venus-like world. Long before the sun leaves the main sequence, our planet will have become uninhabitable by any life form we would recognize. The sun's eventual departure from the main sequence, roughly 5 billion years from now, will mark the beginning of dramatic changes in its structure and appearance. As the hydrogen in the core is exhausted, fusion will shift to a shell surrounding the helium-rich core, causing the outer layers to expand and cool. The sun will become a red giant, swelling to perhaps 100 times its current diameter and engulfing the inner planets, including Earth. But that fate lies far in the future. For now, the sun continues its steady burning, providing the light and warmth that sustain life on our small planet. Each second, the sun converts roughly 600 million tons of hydrogen into helium, releasing energy equivalent to billions of nuclear weapons. This energy streams outward through space, a tiny fraction of it intercepting Earth and driving the complex systems of atmosphere, ocean, and biosphere that make our world unique. The sun rises and sets, marking the passage of days. Its position in the sky shifts with the seasons, governing the rhythms of agriculture and migration. Its light enables photosynthesis, the process by which plants convert carbon dioxide and water into the sugars that form the base of nearly every food chain on Earth. Without the sun, our planet would be a frozen, lifeless rock drifting through the darkness of space. Yet the sun is more than just a source of energy. It is also a natural laboratory for studying physics under conditions impossible to replicate on Earth. Solar observations have revealed phenomena ranging from the oscillations that probe the solar interior to the magnetic reconnection, events that power flares and coronal mass ejections. The sun serves as a Rosetta Stone for understanding other stars, providing detailed information that can be extrapolated to objects too distant for such close study. Space missions have transformed our understanding of the Sun over the past several decades. The Solar and Heliospheric Observatory, launched in 1995, has provided continuous observations of the Sun for more than 25 years, tracking solar activity through more than 2 complete cycles. The Solar Dynamics Observatory, launched in 2010, images the Sun in multiple wavelengths every 12 seconds, revealing the dynamic behavior of the solar atmosphere in unprecedented detail. And the Parker Solar Probe, launched in 2018, is gradually spiraling closer to the Sun, eventually approaching within 6 million kilometers of the solar surface, closer than any spacecraft has ever ventured. These missions have revealed a Sun far more dynamic and complex than earlier generations imagined. The corona is constantly restructuring itself, with magnetic loops rising, expanding, and reconnecting on timescales of minutes to hours. The solar wind is not uniform, but structured into fast and slow streams that interact as they propagate outward. And the Sun's magnetic field is not a simple dipole, but a complex evolving structure that defies easy characterization. As we contemplate our star, we might feel a sense of gratitude for its steady, reliable output. The Sun has provided a stable energy source for billions of years, allowing life to emerge and evolve on at least one of its planets. It will continue to shine for billions of years more, though eventually its fuel will run out, and it will enter the final stages of stellar evolution. For now, we bask in its warmth, study its behavior, and marvel at the nuclear furnace that makes our existence possible. In the grand census of stars that populate our galaxy, no type is more numerous than the red dwarfs. These small, cool stars comprise roughly 70% of all stars in the Milky Way, yet their dimness renders them invisible to the naked eye. The nearest star to our Sun, Proxima Centauri, is a red dwarf, as is Barnard's star, the second nearest stellar system. These diminutive objects may lack the brilliance of their more massive cousins, but their extraordinary longevity and sheer abundance make them among the most important stars in the cosmos. Red dwarfs are defined as main sequence stars with masses between roughly 8% and 50% that of our Sun. Below 8% of solar mass, an object lacks sufficient gravitational compression to sustain hydrogen fusion in its core, and it becomes a brown dwarf-failed star that glows dimly from the heat of its formation but never achieves true stellar status. Above 50% of solar mass, stars become hot enough to leave the red dwarf category, transitioning into the orange K-type stars that bridge the gap between red dwarfs and Sun-like stars. The surface temperatures of red dwarfs range from approximately 2,000 to 3,500 degrees Kelvin, making them the coolest of all main sequence stars. These temperatures are low enough that molecules can exist intact in the stellar atmosphere compounds, like titanium oxide and vanadium oxide, which would be torn apart by the heat of hotter stars, produce prominent absorption features in red dwarf spectra. The presence of these molecular bands gives red dwarf spectra a distinctive appearance that allows astronomers to identify these stars even at great distances. The luminosities of red dwarfs are correspondingly low, ranging from roughly 1/10,000th to 1/10th that of the Sun. The dimmest red dwarfs produce so little light that they would need to be brought within a few light years of Earth to be visible to the naked eye. Even Proxima Centauri, at a distance of just over 4 light years, has an apparent magnitude of roughly 11 far too faint to see without a telescope. The brightest known red dwarf, a star called Ax Microscopiae, has a visual magnitude of only 6.7, hovering right at the threshold of naked eye visibility under perfect conditions. This extreme faintness explains why red dwarfs remained largely unknown until the 20th century, despite being the most common type of star in the galaxy. Early astronomers, limited to what they could see with their eyes or small telescopes, naturally focused on the bright stars that dominate the night sky. These bright stars, the blue and white giants, the yellow stars like our Sun, are actually quite rare, comprising only a small fraction of the total stellar population. The red dwarfs that make up the majority of stars remained hidden in the darkness, their feeble light lost against the glare of their more luminous neighbours. The physical dimensions of red dwarfs are as modest as their luminosities. The smallest red dwarfs have radii only about 10% that of the Sun, making them not much larger than the planet Jupiter. The largest red dwarfs approach 60% of the solar radius, still considerably smaller than our star. Despite their small sizes, red dwarfs are remarkably dense, with the smallest examples packing their mass into such compact volumes that their average densities exceed that of the Sun by factors of 10 or more. The internal structure of red dwarfs differs fundamentally from that of more massive stars. In the Sun, energy generated in the core is transported outward, first by radiation, then by convection in the outer layers. The radiative zone acts as a barrier, preventing the mixing of core material with the outer envelope. In red dwarfs below about 35% of solar mass, this radiative zone disappears entirely. The entire star becomes convective, with hot plasma circulating from the core all the way to the surface. This fully convective structure has profound implications for red dwarf evolution. In stars like the Sun, the helium produced by nuclear fusion accumulates in the core, unable to mix with the hydrogen-rich envelope above. Over time, this creates a helium-rich core that eventually triggers dramatic changes in stellar structure. In fully convective red dwarfs, by contrast, the fusion products are continuously mixed throughout the star, preventing the formation of a distinct helium core and allowing the star to burn a much larger fraction of its total hydrogen supply. The nuclear reactions in red dwarf cores proceed at a leisurely pace compared to more massive stars. The core temperatures, while still measured in millions of degrees, are lower than in the Sun, and the fusion rates are correspondingly reduced. A red dwarf with 1/10 of the mass of the Sun produces only about 1/10,000th as much energy, burning through its hydrogen fuel with extraordinary slowness. This combination of efficient fuel usage and low consumption rates gives red dwarfs lifetimes that dwarf those of all other stellar types. The smallest red dwarfs will shine for trillions of years, periods so vast that they exceed the current age of the universe by factors of 100 or more. No red dwarf that has ever formed has yet had time to exhaust its hydrogen fuel and leave the main sequence. The oldest red dwarfs in the galaxy, born more than 10 billion years ago in the earliest epochs of star formation, are still in the prime of their lives, with more than 99% of their existence still ahead of them. These ancient stars will continue shining long after the last massive blue giants have exploded and faded, serving as the final stellar inhabitants of an aging cosmos. The longevity of red dwarfs raises intriguing possibilities for the far future of the universe. In the current epoch, the cosmos is filled with stars of all types, from brilliant blue supergiants to dim red dwarfs. But this diversity is temporary. The massive stars burn out quickly, exploding as supernovae or collapsing into black holes within mere millions of years. Sun-like stars last longer but still exhaust their fuel within 10 billion years or so. Only the red dwarfs persist, their feeble fires burning steadily across the eons. In the distant future, trillions of years from now, red dwarfs will be the only stars still shining. The universe will have grown dark and cold, its expansion having carried most galaxies beyond the visible horizon. The remaining galaxies will have merged into vast elliptical systems, their gas supplies exhausted and their star formation long since ceased. Against this backdrop of cosmic twilight, the red dwarfs will continue their patient burning, the last sources of starlight in an aging universe. Eventually, even the red dwarfs will exhaust their fuel. The smallest and longest lived will finally convert the last of their hydrogen to helium, their cores contracting and cooling as fusion sputters and dies. These stellar embers will become helium white dwarfs, slowly radiating away their residual heat over timescales that make their main sequence lifetimes seem brief by comparison. The era of starlight will finally end, giving way to an epoch of darkness, broken only by the occasional flash of a stellar collision or the slow decay of matter itself. But that ultimate darkness lies inconceivably far in the future. For now, red dwarfs continue to form in stellar nurseries throughout the galaxy, adding to the vast population that already exists. Each new red dwarf that ignites begins a journey that will span trillions of years, outlasting not only its more massive siblings, but also the galaxies, galaxy clusters, and large-scale structures that define the current cosmic landscape. In their patient persistence, red dwarfs embody a kind of cosmic endurance that dwarfs any human conception of time. The nearest red dwarf to our solar system is Proxima Centauri, a small star located approximately 4.2 light-years away in the Alpha Centauri system. Proxima is gravitationally bound to the binary pair Alpha Centauri A and B, orbiting them at a distance of roughly 13,000 astronomical units, so far that it takes more than 500,000 years to complete a single orbit. Despite this enormous separation, the three stars share a common origin, having formed together from the same molecular cloud more than 4 billion years ago. Proxima Centauri has a mass of roughly 12% that of the Sun, and a radius about 14% of solar. Its surface temperature hovers around 3,000 degrees Kelvin, giving it a deep red colour that would be visible if the star were bright enough to see with the naked eye. The luminosity of Proxima is only about 1/6 of 1% that of the Sun, meaning that a planet would need to orbit very close to the star to receive Earth-like amounts of energy. In 2016, astronomers announced the discovery of a planet orbiting Proxima Centauri in just such a close orbit. Proxima Centauri b, as the planet is called, has a minimum mass roughly 1.3 times that of Earth and orbits its star at a distance of only about 7.5 million kilometres, roughly 5% of the Earth-Sun distance. At this proximity, the planet completes an orbit in just 11.2 Earth days, yet it receives roughly the same amount of energy from Proxima as Earth receives from the Sun. The discovery of Proxima b sparked intense interest in the habitability of planets around red dwarfs. These stars are so numerous that if even a small fraction of them host habitable planets, the total number of potentially life-bearing worlds in the galaxy could be enormous. Yet red dwarfs present challenges for habitability that do not exist around Sun-like stars, and the question of whether life could thrive on a planet like Proxima b remains open. One challenge involves the close orbits required for habitable zone planets around red dwarfs. At such small distances, tidal forces from the star are strong enough to synchronize the planet's rotation with its orbit, a phenomenon called tidal locking. A tidally locked planet always shows the same face to its star, creating a permanent day side and a permanent night side. The day side would experience eternal noon, with the star fixed at the same point in the sky, while the night side would know only eternal darkness. The climate of a tidally locked planet would differ dramatically from Earth's. Without the day-night cycle that distributes heat around our planet, Temperature extremes between the day side and night side could be severe. The day side might become scorchingly hot while the night side freezes, with habitable conditions existing only in a narrow twilight zone around the terminator, the boundary between light and dark. Atmospheric circulation could moderate these extremes, transporting heat from day side to night side. But the effectiveness of this redistribution depends on atmospheric properties that remain uncertain. Another challenge for habitability around red dwarfs involves stellar activity. Despite their cool temperatures and low luminosities, red dwarfs can be surprisingly violent stars, producing powerful flares that temporarily increase their brightness by factors of 10 or more. These flares release intense bursts of ultraviolet and X-ray radiation that could strip away planetary atmospheres and sterilize surfaces. Young red dwarfs are particularly active, with flare rates that would subject any orbiting planets to frequent radiation bombardment. Proxima Centauri itself is known to be an active flare star, producing outbursts that briefly increase its brightness by significant amounts. In 2019, astronomers detected a superflare from Proxima that was roughly 100 times more powerful than any flare ever observed from our Sun. Such events would deliver potentially lethal doses of radiation to any unprotected life on Proxima b, raising questions about whether the planet could retain an atmosphere or support life on its surface. Yet the picture is not entirely bleak. Red dwarf activity decreases with age as the stars gradually spin down and their magnetic dynamos weaken. Proxima Centauri, at roughly 5 billion years old, is less active than it was in its youth, and its flare rate will continue to decline over the coming billions of years. A planet that survived the active early phase might find conditions improving as its star settles into a more quiescent middle age. Furthermore, life on a red dwarf planet need not be confined to the surface. Subsurface oceans, protected from radiation by layers of ice or rock, could provide stable environments for life, regardless of surface conditions. On Earth, thriving ecosystems exist around deep-sea hydrothermal vents, completely independent of sunlight and surface conditions. Similar environments might exist on planets throughout the galaxy, hidden beneath hostile surfaces, but potentially teeming with life. The second nearest stellar system to our Sun also contains a red dwarf Barnard star, located roughly 6 light-years away in the constellation Ophiuchus. This star is named after the American astronomer Edward Emerson Barnard, who discovered its remarkably high proper motion in 1916. Barnard's star moves across the sky faster than any other star, covering a distance equal to the Moon's diameter roughly every 180 years. This rapid motion reflects the star's proximity to the Sun and its relatively high velocity through space. Barnard's star is older than Proxima Centauri, with an estimated age of roughly 10 billion years, more than twice the age of our solar system. This advanced age has allowed the star to spin down considerably, reducing its magnetic activity and flare rate compared to younger red dwarfs. The star's surface temperature is approximately 3,100 degrees Kelvin, and its luminosity is only about 0.3%, that of the Sun. In 2018, astronomers announced evidence for a planet orbiting Barnard's star, though subsequent observations have cast doubt on this detection. The putative planet, if it exists, would have a mass roughly 3 times that of Earth and would orbit at a distance that places it well outside the star's habitable zone. The surface temperature of such a world would be roughly minus 150 degrees Celsius, far too cold for liquid water to exist on the surface. However, internal heat from radioactive decay or tidal forces could potentially maintain subsurface liquid water, as may occur on some moons in our own solar system. The abundance of red dwarfs in the solar neighbourhood reflects their dominance throughout the galaxy. Within 10 parsecs of the Sonosphere, containing roughly 350 known stellar objects, red dwarfs account for more than 230 entries, or roughly 69% of the total. This fraction likely underestimates the true proportion, as the faintness of red dwarfs makes them difficult to detect even at relatively short distances. Ongoing surveys continue to discover new red dwarfs in the solar neighbourhood, gradually filling in our census of nearby stars. The Recon survey, which aims to identify all stellar objects within 10 parsecs of the Sun, has been particularly productive in finding nearby red dwarfs. Using careful measurements of stellar positions over time, the survey determines distances through the classic technique of trigonometric parallax, the apparent shift in a star's position as Earth orbits the Sun. This method provides direct distance measurements without relying on assumptions about stellar properties, making it the gold standard for nearby star distances. As our census of nearby red dwarfs improves, so does our understanding of their properties and the planets they host. The Kepler Space Telescope, though primarily designed to find planets around Sun-like stars, also detected numerous planets orbiting red dwarfs. The TS mission, launched in 2018, specifically targets nearby red dwarfs for planet searches, taking advantage of their small sizes to detect Earth-sized planets through the transit method. And ground-based surveys using the radial velocity technique have found dozens of planets around nearby red dwarfs, including several in or near the habitable zones of their stars. The emerging picture suggests that planets are common around red dwarfs, perhaps even more common than around Sun-like stars. Statistical analyses of Kepler data indicate that the average red dwarf hosts at least one planet, with many hosting multiple planets in compact orbital configurations. Rocky planets in the habitable zones of red dwarfs may number in the tens of billions throughout the Milky Way alone, making them potentially the most common sites for habitable conditions in the galaxy. Whether any of these worlds actually harbour life remains unknown. The challenges posed by tidal locking, stellar activity, and other factors unique to red dwarf systems may prove insurmountable, leaving these planets as sterile as the Moon. Alternatively, life may prove more adaptable than we imagine, finding ways to thrive under conditions that seem hostile by terrestrial standards. The only way to know for certain is to study these worlds directly, searching for biosignatures in their atmospheres, or eventually sending probes to examine them up close. The red dwarfs, humble and dim though they may be, thus hold a special place in the search for life beyond Earth. Their abundance means that if life can exist around them, it may be extraordinarily common throughout the cosmos. Their longevity means that any life that does arise has trillions of years to evolve and develop, far longer than the few billion years available around Sun-like stars. And their proximity with Proxima Centauri, just over 4 light-years away, means that they offer the most accessible targets for future exploration. As we contemplate these small cool stars, we might find comfort in their patient endurance. The red dwarfs ask nothing of the universe but the chance to burn their hydrogen fuel in peace, converting mass to energy with a steadiness that will outlast galaxies. They are the tortoises of the stellar world, slow and steady, destined to inherit a cosmos that their flashier cousins will have long since departed. In their dim red glow, we see a vision of cosmic persistence that transcends human timescales, a reminder that the universe operates on rhythms far slower and grander than our brief lives can encompass. When a star exhausts the hydrogen fuel in its core, it embarks upon a dramatic transformation that will reshape its structure and appearance beyond recognition. The stable equilibrium that characterized its main sequence existence gives way to a period of rapid change as the star swells to enormous dimensions and its surface cools to a deep red hue. These evolved stars, the red giants and supergiants, represent a brief but spectacular phase of stellar life, a final flourishing before the star meets its ultimate fate. The transition from main sequence to giant begins when the hydrogen in the stellar core is finally depleted. Throughout the main sequence phase, nuclear fusion has been converting hydrogen to helium, gradually building up a helium-rich core at the center of the star. This core is inert. The temperatures and pressures are insufficient to fuse helium into heavier elements, but it continues to grow as hydrogen burning proceeds in a shell surrounding it. When the core hydrogen is exhausted, the nuclear reactions that have supported the star against gravity suddenly cease. The core, no longer generating energy, begins to contract under its own weight. This contraction releases gravitational energy, heating the surrounding layers and causing hydrogen fusion to ignite in a shell around the inert helium core. The shell burning produces more energy than the core burning did, and this excess energy causes the outer layers of the star to expand dramatically. As the star expands, its surface moves farther from the hot interior, and the temperature drops accordingly. A star that was yellow or white on the main sequence becomes orange, then red, as its surface cools from thousands of degrees to perhaps 3,000 or 4,000. The star has become a red giant, its bloated envelope extending to dimensions that would engulf the inner planets of our solar system. The expansion of a red giant is truly remarkable in scale. A sun-like star, currently about 1.4 million kilometers in diameter, will eventually swell to roughly 100 times. This size large enough that, if placed at the center of our solar system, its surface would extend beyond the orbit of Mercury and perhaps approach that of Venus. The most extreme red giants grow even larger, with diameters exceeding 1 astronomical unit, the distance from Earth to the Sun. Despite their enormous sizes, red giants are not particularly massive. The expansion occurs at nearly constant mass, meaning that the density of the stellar envelope drops precipitously. The outer layers of a red giant are so tenuous that they would qualify as a laboratory vacuum on Earth, with densities millions of times lower than the air we breathe. Only the core remains dense, a compact ball of helium surrounded by a vast diffuse envelope of hydrogen-rich gas. The appearance of a red giant in the night sky is distinctive and beautiful. The cool surface temperature produces a deep orange or red colour that contrasts sharply with the blue and white of hotter stars. Several of the brightest stars visible to the naked eye are red giants, including Arcturus in the constellation Boötes and Aldebaran in Taurus. These stars shine with luminosities tens or hundreds of times greater than the Sun, their brilliance arising from their enormous surface areas rather than high surface temperatures. Arcturus, the fourth brightest star in the night sky, provides an excellent example of a red giant in its prime. Located roughly 37 light-years from Earth, Arcturus has a diameter about 25 times that of the Sun and a luminosity roughly 170 times greater. Its surface temperature of approximately 4,300 degrees Kelvin gives it a distinctive orange colour that is easily visible to the naked eye. Arcturus is believed to be roughly 7 billion years old, having exhausted its core hydrogen and begun its giant phase perhaps 1 billion years ago. Aldebaran, the brightest star in Taurus and the 14th brightest in the night sky, is another prominent red giant. At a distance of roughly 65 light-years, Aldebaran has swollen to approximately 44 times the Sun's diameter and shines with a luminosity about 500 times greater. Its orange-red colour marks it as a cool giant, with a surface temperature around 3,900 degrees Kelvin. Aldebaran appears to lie within the Hyades star cluster, but this is a line-of-sight coincidence. The star is actually much closer to Earth than the cluster members. The red giant phase is relatively brief compared to the main sequence lifetime. A Sun-like star spends roughly 10 billion years on the main sequence, but only about 1 billion years as a red giant. More massive stars evolve even faster, with the most massive spending only a few million years in the giant phase. This brevity explains why red giants, though prominent in the night sky, are relatively rare compared to main sequence stars. At any given moment, most stars are still burning hydrogen in their cores. As a red giant evolves, its internal structure continues to change. The helium core grows steadily as hydrogen shell burning adds more helium ash. The core contracts and heats, approaching the temperature threshold at which helium fusion can begin. For stars less than about 2 solar masses, this threshold is reached suddenly and dramatically in an event called the helium flash. The helium flash occurs when the core temperature reaches approximately 100 million degrees Kelvin, hot enough for helium nuclei to fuse into carbon through a process called the triple alpha reaction. In this reaction, 3 helium nuclei, also called alpha particles, combine to form a single carbon nucleus, releasing energy in the process. The reaction is highly temperature sensitive, and when it finally ignites in the degenerate core of a low-mass red giant, it runs away explosively. The helium flash releases an enormous amount of energy in a very short time, perhaps as much as 100 billion times the sun's current luminosity for a few seconds. Yet this tremendous outburst remains hidden from external view, as the energy is absorbed by the overlying layers and goes into lifting the degeneracy of the core rather than escaping as radiation. The star's appearance changes little during the flash itself, though the aftermath brings significant restructuring of the stellar interior. Following the helium flash, the star settles into a new equilibrium with helium burning steadily in the core and hydrogen burning in a surrounding shell. This phase, called the horizontal branch in the Hertzsprung-Russell diagram, is more stable than the preceding red giant phase, but still relatively brief. The star may shrink somewhat and heat up, moving leftward on the HR diagram, before eventually exhausting its core helium and beginning another round of expansion. More massive stars, those above roughly 2 solar masses, avoid the helium flash because their cores never become degenerate. In these stars, helium ignition occurs more gradually, without the explosive runaway that characterizes lower mass stars. The subsequent evolution is similar, however, with the star eventually exhausting its core helium and expanding once again. The most massive stars, those above roughly 8 solar masses, follow a different evolutionary path entirely. These stellar giants are so luminous that they never develop the deep convective envelopes characteristic of red giants. Instead, they expand and cool more modestly, becoming yellow or blue supergiants rather than red giants. Their evolution is driven by a succession of nuclear burning stages, each shorter than the last, as the star fuses progressively heavier elements in its core. Supergiants represent the most extreme examples of stellar expansion. These massive luminous stars can grow to truly enormous dimensions, with diameters measured in astronomical units rather than solar radii. The largest known stars are red supergiants, bloated objects that would extend beyond the orbit of Jupiter if placed at the centre of our solar system. These stellar behemoths are among the most impressive objects in the cosmos, their sheer scale defying easy comprehension. Betelgeuse, the bright red star marking the shoulder of Orion, is perhaps the most famous red supergiant. Located roughly 700 light-years from Earth, Betelgeuse has a diameter estimated at roughly 700 to 1,000 times. that of the Sun so large that its surface would extend well beyond the orbit of Mars and possibly beyond the asteroid belt. The star's luminosity is roughly 100,000 times that of the Sun, making it one of the most luminous stars visible to the naked eye. Betelgeuse is also one of the few stars large enough and close enough for its surface to be directly imaged by modern telescopes. These images reveal a mottled, irregular surface marked by enormous convective cells and bright spots. The star's appearance changes over time as these surface features evolve, contributing to the irregular brightness variations that have been observed for centuries. Betelgeuse is classified as a semi-regular variable star, with brightness changes of roughly 1 magnitude occurring over periods of roughly 400 days. In late 2019 and early 2020, Betelgeuse underwent an unprecedented dimming event that captured worldwide attention. The star faded to roughly 1/3 of its normal brightness, dropping from one of the 10 brightest stars in the sky to barely making the top 20. Speculation ran rampant that the star might be about to explode as a supernova, though astronomers cautioned that such an event, while inevitable, was not necessarily imminent. Subsequent observations revealed that the dimming was caused by a combination of factors: a natural minimum in the star's pulsation cycle, coinciding with the ejection of a large cloud of dust that partially obscured the star from Earth's view. The dust cloud, expelled from the star's outer layers, cooled and condensed as it moved away from the stellar surface, blocking a significant fraction of the star's light. By mid-2020, Betelgeuse had returned to its normal brightness, and the supernova speculation subsided, though the star remains a prime candidate for the next naked-eye supernova in our galaxy. Another famous red supergiant is Antares, the brightest star in the constellation Scorpius. The name Antares means rival of Mars in Greek, a reference to the star's red colour and brightness, which can rival that of the red planet when Mars is near opposition. Antares lies roughly 550 light-years from Earth and has a diameter roughly 700 times that of the Sun. Like Betelgeuse, Antares is a semi-regular variable star with brightness fluctuations occurring over periods of several years. The red supergiants are doomed stars, approaching the end of their brief but brilliant lives. Having exhausted the hydrogen in their cores and begun burning helium and heavier elements, they have only a few million years remaining before their cores collapse, and they explode as supernovae. The exact timing of these explosions is impossible to predict. The internal processes that trigger core collapse are hidden from view, and the external appearance of the star provides few clues about its imminent fate. Blue supergiants represent a different evolutionary state, one that massive stars may pass through either before or after the red supergiant phase. These hot, luminous stars have surface temperatures exceeding 10,000 degrees Kelvin, giving them blue or blue-white colours. Their luminosities can exceed 100,000 times that of the Sun, making them visible across vast distances. Rigel, the brightest star in Orion, is a blue supergiant, as is Deneb, the brightest star in Cygnus. Rigel, located roughly 860 light-years from Earth, is one of the most luminous stars in our region of the galaxy. With a luminosity roughly 120,000 times that of the Sun, Rigel would be visible to the naked eye from a distance of several thousand light-years. Its surface temperature of approximately 12,000 degrees Kelvin gives it a brilliant blue-white colour that contrasts sharply with the red of Betelgeuse on the opposite side of Orion. Deneb, marking the tail of Cygnus the Swan, is even more luminous than Rigel, though its greater distance, roughly 2,500 light-years, makes it appear somewhat fainter. Estimates of Deneb's luminosity range from roughly 100,000 to 200,000 times that of the Sun, making it one of the most intrinsically bright stars visible to the naked eye. If Deneb were as close to Earth as Sirius, it would be bright enough to cast shadows. The stellar winds from supergiants are among the most powerful in the cosmos. These massive stars lose mass at prodigious rates, shedding their outer layers into space at velocities of hundreds to thousands of kilometers per second. A red supergiant like Betelgeuse loses roughly 1 solar mass every 10,000 years, a rate that would strip the Sun of its entire mass in a cosmically brief instant. This mass loss shapes the star's subsequent evolution and creates the circumstellar environments that will later be illuminated by supernova explosions. The material shed by supergiants enriches the interstellar medium with heavy elements forged in the stellar interior. Carbon, nitrogen, oxygen, and other elements produced by nuclear fusion are carried away by the stellar wind, seeding the galaxy with the raw materials for future generations of stars and planets. The dust grains that form in the cooling outflows provide surfaces for chemical reactions and serve as the building blocks for rocky planets like Earth. As we contemplate the giants and supergiants, we witness stars in their twilight years, burning through their remaining fuel with profligate abandon. These bloated, luminous objects represent a brief but spectacular phase of stellar evolution, a final flourishing before the star meets its ultimate fate. Whether they end as white dwarfs, neutron stars, or black holes, the giants and supergiants leave lasting legacies in the elements they create and disperse, the nebulae they illuminate, and the cosmic recycling they enable. Every star that shines in the night sky is destined to die. The nuclear fires that sustain stellar luminosity cannot burn forever. Eventually, the fuel runs out, and the star must face its final transformation. For stars like our Sun, this ending is neither sudden nor violent, but rather a gradual fading, a slow transition from brilliant beacon to cooling ember. The death of a sun-like star unfolds over millions of years, producing some of the most beautiful objects in the cosmos before finally yielding a dense, Earth-sized remnant that will persist for trillions of years. The journey towards stellar death begins when the hydrogen fuel in the core is exhausted. As we have seen, this triggers the expansion of the star into a red giant, with hydrogen burning continuing in a shell around the inert helium core. The core itself contracts and heats until, at temperatures around 100 million degrees, helium fusion ignites in the dramatic helium flash. The star then settles into a new equilibrium, burning helium in its core, while hydrogen continues to burn in an outer shell. Helium fusion proceeds through the triple alpha process, combining 3 helium nuclei to form carbon. Some of this carbon captures additional helium nuclei to form oxygen, so the products of helium burning are a mixture of carbon and oxygen. The energy yield from helium fusion is less than from hydrogen fusion, and the process proceeds more rapidly. A sun-like star will exhaust its core helium in roughly 100 million years, compared to the 10 billion years spent burning hydrogen. When the core helium is exhausted, the star faces a crisis. The carbon-oxygen core that remains is too cool to ignite further fusion reactions. Carbon burning requires temperatures of roughly 500 million degrees, far higher than a sun-like star can achieve. Without a new energy source, the core contracts under its own gravity, heating the surrounding layers and triggering a complex series of events that will ultimately expel the star's outer envelope. The star enters a phase called the asymptotic giant branch, or AGB, characterized by extreme instability and dramatic changes in structure. 2 nuclear burning shells, 1 burning hydrogen, 1 burning helium surround the inert carbon-oxygen core. These shells do not burn steadily, but instead alternate in a series of thermal pulses, with the helium shell periodically igniting in brief intense flashes that temporarily increase the star's luminosity by factors of thousands. During the thermal pulses, convection dredges material from the interior to the surface, enriching the stellar atmosphere with carbon and other elements produced by nuclear burning. Some AGB stars become carbon stars, with more carbon than oxygen in their atmospheres, a reversal of the normal cosmic abundance ratio. These carbon-rich stars have distinctive red colours and spectra marked by molecular bands of carbon compounds, making them easily identifiable in surveys of stellar populations. The AGB phase is also characterised by intense mass loss, as the star sheds its outer layers into space at rates far exceeding the solar wind. This mass loss is driven by a combination of pulsations and radiation pressure on dust grains that form in the cool outer atmosphere. The pulsations lift material away from the stellar surface, where it cools and condenses into dust. Radiation from the star then pushes on the dust grains, accelerating them outward and dragging the surrounding gas along. The mass loss rates during the AGB phase can reach 1 solar mass per 100,000 years, 10 million times greater than the current solar wind. At these rates, a sun-like star can shed most of its envelope in just a few 100,000 years, leaving behind only the hot, dense core. This stripping of the outer layers is the key process that transforms an AGB star into a planetary nebula and white dwarf. As the envelope is stripped away, the hot core is gradually exposed. The surface temperature rises as successively deeper, hotter layers are revealed, eventually reaching tens of thousands of degrees. At these temperatures, the core emits copious ultraviolet radiation that ionizes the surrounding gas, causing it to glow with the characteristic colours of a planetary nebula. Planetary nebulae are among the most beautiful objects in the cosmos, their intricate shapes and vivid colours making them favourite targets for both amateur and professional astronomers. The name is a historical misnomer. These objects have nothing to do with planets, but were so named by early observers who thought their round, fuzzy appearance resembled the disks of planets seen through small telescopes. We now know that planetary nebulae are the expelled envelopes of dying stars, illuminated by the ultraviolet radiation of the exposed stellar core. The shapes of planetary nebulae are remarkably diverse, ranging from simple spherical shells to complex bipolar structures with multiple lobes and jets. This diversity reflects the varied circumstances under which the nebulae form. The presence of binary companions, magnetic fields, and rotation can all influence the geometry of the mass loss and the resulting nebula shape. Some planetary nebulae display remarkable symmetry, with mirror image lobes extending in opposite directions from the central star. Others are chaotic and irregular, suggesting turbulent or episodic mass loss. The Ring Nebula in the constellation Lyra is one of the most famous planetary nebulae, easily visible through small telescopes as a small smoky ring surrounding a faint central star. Located roughly 2,300 light-years from Earth, the Ring Nebula has a diameter of roughly 1 light-year and is expanding at approximately 20 kilometers per second. The central star, with a surface temperature of roughly 120,000 degrees, is one of the hottest stars known. Its intense ultraviolet radiation responsible for the nebula's glow. The Helix Nebula in Aquarius is the closest bright planetary nebula to Earth, lying at a distance of roughly 650 light-years. Its proximity makes it appear large in the sky, roughly half the diameter of the full moon, earning it the nickname the Eye of God for its striking appearance in deep photographs. The Helix Nebula displays a complex structure of concentric rings and radial streamers, suggesting multiple episodes of mass loss from the central star. The streamers, sometimes called cometary knots, point away from the central star like the tails of countless tiny comets, sculpted by the intense radiation and stellar wind from the hot core. The Cat's Eye Nebula in the constellation. Draco represents one of the most structurally complex planetary nebulae known. Its intricate pattern of concentric shells, jets, and knots has puzzled astronomers for decades, suggesting a formation history far more complicated than simple spherical mass loss. The most likely explanation involves a binary companion to the central star, whose gravitational influence shaped the outflowing material into the observed patterns. The Cat's Eye serves as a reminder that stellar death, like stellar life, can be profoundly influenced by the presence of nearby companions. The Butterfly Nebula, also known as NGC 6302, displays one of the most dramatic bipolar structures among planetary nebulae. Two enormous lobes of gas extend in opposite directions from a hidden central star, their shapes resembling the wings of a cosmic butterfly. The central star is one of the hottest known, with a surface temperature exceeding 200,000 degrees, yet it remains invisible in optical light, shrouded by a dense disk of dust that girdles its equator. The lobes are expanding at velocities exceeding 600 kilometers per second, among the fastest outflows observed in any planetary nebula. The colours of planetary nebulae arise from the emission of light by ionized atoms in the nebula gas. Different elements emit light at characteristic wavelengths, producing the distinctive hues visible in photographs. The green colour that dominates many planetary nebulae comes from doubly ionized oxygen, which emits strongly at wavelengths around 500 nanometers. Red colours typically arise from hydrogen and nitrogen emission, while blue hues indicate the presence of helium or highly ionized oxygen. By analysing the colours and spectra of planetary nebulae, astronomers can determine the chemical composition of the expelled material and trace the nuclear processing that occurred in the parent star. The lifetimes of planetary nebulae are brief by astronomical standards. The expanding gas disperses into the surrounding interstellar medium within roughly 20,000 years, fading from view as it becomes too diffuse to emit detectable light. The central star, meanwhile, continues to cool and fade, its nuclear fires extinguished and its luminosity sustained only by the slow release of residual thermal energy. Within a few tens of thousands of years, the brilliant planetary nebula has vanished, leaving behind only a dim white dwarf and a slight enrichment of the local interstellar medium. White dwarfs are the final remnants of sun-like stars, the dense cores left behind after the planetary nebula phase. These objects pack roughly the mass of the Sun into a volume comparable to Earth, creating densities millions of times greater than any material on our planet. A teaspoon of white dwarf material would weigh several tons on Earth, its atoms crushed together so tightly that the electrons are stripped from their nuclei and form a degenerate gas that resists further compression. The physics of white dwarfs is governed by a quantum mechanical phenomenon called electron degeneracy pressure. In ordinary matter, atoms maintain their spacing through the electrical repulsion between their electron clouds. In a white dwarf, the matter is so compressed that this normal atomic structure breaks down. The electrons are squeezed into the smallest possible volume allowed by the laws of quantum mechanics. The Pauli exclusion principle, which forbids two electrons from occupying the same quantum state, creates an outward pressure that supports the white dwarf against gravitational collapse. This degeneracy pressure has a remarkable property. It does not depend on temperature. Unlike the thermal pressure that supports main sequence stars, which would decrease if the star cooled, degeneracy pressure remains constant regardless of the white dwarf's temperature. This means that a white dwarf can cool indefinitely without collapsing further, slowly radiating away its thermal energy over billions of years while maintaining its size and density. The cooling of white dwarfs follows a predictable pattern that astronomers can use to estimate their ages. A newly formed white dwarf has a surface temperature of roughly 100,000 degrees, making it blue-white in colour and quite luminous despite its small size. Over millions of years, the surface cools to tens of thousands of degrees, then thousands of degrees, the colour shifting from blue to white to yellow to orange to red. The oldest white dwarfs in the galaxy have been cooling for more than 10 billion years and now have surface temperatures of only a few thousand degrees, barely warmer than the filament of an incandescent light bulb. The relationship between white dwarf temperature and age provides a powerful tool for dating stellar populations. By measuring the temperatures of the coolest white dwarfs in a star cluster or galaxy, astronomers can determine when star formation began in that system. This technique has been applied to globular clusters, the ancient spherical collections of stars that orbit the Milky Way, yielding ages of roughly 12 to 13 billion years, consistent with other methods of dating the oldest structures in the universe. White dwarfs have a maximum mass known as the Chandrasekhar limit of approximately 1.4 solar masses. Above this limit, electron degeneracy pressure cannot support the star against gravitational collapse, and the white dwarf would implode into a neutron star or black hole. This limit was calculated by the Indian-American astrophysicist Subrahmanyan Chandrasekhar in 1930, when he was just 19 years old, earning him a share of the Nobel Prize in Physics more than 50 years later. The Chandrasekhar limit has profound implications for stellar evolution. Stars that begin their lives with masses up to roughly 8 solar masses can shed enough material during the giant and planetary nebula phases to leave behind white dwarfs below the limit. More massive stars cannot lose enough mass and are destined for more violent endings as supernovae. The limit also plays a crucial role in a particular type of stellar explosion called a Type Ia supernova, which occurs when a white dwarf in a binary system accretes enough material from its companion to exceed the Chandrasekhar mass. The composition of a white dwarf depends on the mass of its progenitor star. The most common white dwarfs have cores of carbon and oxygen, the products of helium burning in stars like our Sun. Less massive progenitors, which never ignite helium burning, leave behind helium white dwarfs, while the most massive progenitors that still avoid core collapse produce oxygen neon magnesium white dwarfs. The surface composition may differ from the core, as gravitational settling causes heavier elements to sink while lighter elements float to the top. Sirius B, the companion to the brightest star in the night sky, was the first white dwarf to be discovered. In 1844, the German astronomer Friedrich Bessel noticed that Sirius was wobbling slightly in its motion across the sky, suggesting the presence of an unseen companion. The companion was finally observed directly in 1862 by the American telescope maker Alvan Graham Clark, who saw a faint star very close to brilliant Sirius. Subsequent observations revealed that this faint companion was extraordinarily dense, packing nearly the mass of the Sun into a volume smaller than Earth. Today, thousands of white dwarfs are known, and they are recognized as one of the most common types of stellar remnant in the galaxy. The Milky Way contains an estimated 10 billion white dwarfs, the accumulated remnants of all the Sun-like stars that have completed their evolution over the galaxy's history. These objects will persist for trillions of years, slowly cooling and fading, but never disappearing entirely. In the far future, when the last stars have burned out and the universe has grown dark and cold, the white dwarfs will remain as frozen relics of the stellar era, their carbon and oxygen cores crystallizing into cosmic diamonds drifting through the void. The fate of our own sun is now clear. In roughly 5 billion years, the hydrogen fuel in the solar core will be exhausted, and the sun will begin its transformation into a red giant. The expanding outer layers will engulf Mercury and Venus, and Earth will be scorched by the increased luminosity, even if it escapes being swallowed entirely. The sun will shed its outer layers in a planetary nebula, briefly illuminating the surrounding space with the ghostly glow of ionized gas. And at the center will remain a white dwarf, a dense ember containing most of the sun's original mass, cooling slowly over the eons as the solar system fades into darkness. This fate, while dramatic, is gentle compared to the violent deaths that await more massive stars. The sun will not explode, will not collapse into a neutron star or black hole, will not send shockwaves rippling through the interstellar medium. Its death will be a gradual fading, a slow transition from brilliant star to cooling remnant. The elements forged in its core, the carbon and oxygen produced by helium burning, will be dispersed into space, perhaps to be incorporated into future generations of stars and planets. In this way, even in death, the sun will contribute to the ongoing cycle of stellar birth and evolution that has shaped the cosmos since the first stars ignited billions of years ago. While sun-like stars fade gently into white dwarfs, their more massive cousins meet far more dramatic ends. Stars born with masses exceeding roughly 8 times that of the sun are destined to explode as supernovae, cataclysmic events that briefly outshine entire galaxies and scatter heavy elements across vast regions of space. These stellar explosions are among the most energetic phenomena in the universe, releasing more energy in seconds than the sun will produce in its entire 10 billion year lifetime. The path to a supernova begins with the same processes that govern all stellar evolution: nuclear fusion in the core, balanced against gravitational collapse. But massive stars burn hotter and faster than their lower mass counterparts, racing through their fuel supplies in mere millions of years rather than billions. And unlike sun-like stars, which cannot achieve the temperatures necessary to fuse carbon, massive stars continue burning progressively heavier elements, building up an onion-like structure of nested burning shells. After exhausting the hydrogen in its core, a massive star ignites helium burning, producing carbon and oxygen just as in lower mass stars. But the massive star's core is hot enough to ignite carbon burning as well, fusing carbon nuclei together to produce neon, sodium, and magnesium. This carbon-burning phase lasts only about 1,000 years, a mere eye blink compared to the millions of years spent burning hydrogen. When the carbon is exhausted, neon burning begins, lasting only about a year. Oxygen burning follows, consuming the core oxygen in a matter of months. And finally, silicon burning ignites the last stage of nuclear fusion that a star can sustain. Silicon burning produces iron and related elements, but it lasts only about a day before the silicon fuel is exhausted. The star has reached the end of the nuclear road. Iron is the terminus of stellar fusion because it has the most tightly bound nucleus of any element. Fusing iron into heavier elements does not release energy, it requires energy, absorbing heat from the surroundings rather than generating it. A star cannot sustain itself by burning iron. Instead, the iron core simply accumulates, growing steadily as silicon burning adds more iron ash. The core is supported against gravity not by fusion energy, but by electron degeneracy pressure, the same quantum mechanical effect that supports white dwarfs. But there is a crucial difference between the iron core of a massive star and a white dwarf. The iron core is much hotter, with temperatures exceeding 5 billion degrees, and it is growing rapidly as silicon burning continues in the surrounding shell. When the core mass exceeds the Chandrasekhar limit of roughly 1.4 solar masses, electron degeneracy pressure can no longer support it against gravity. The core begins to collapse. The collapse of the iron core is catastrophically rapid. In less than a second, the core implodes from a size comparable to Earth to a dense ball only about 20 kilometers across. The collapse is so violent that protons and electrons are squeezed together to form neutrons, releasing a flood of neutrinos that carry away most of the gravitational energy. The core becomes a neutron star, supported against further collapse by neutron degeneracy pressure, a quantum mechanical effect similar to electron degeneracy, but involving neutrons rather than electrons. The outer layers of the star, suddenly deprived of the support provided by the core, begin to fall inward, but they encounter the newly formed neutron star, which acts like a solid wall, bouncing the infalling material back outward. This bounce, combined with energy deposited by the flood of neutrinos, drives a powerful shock wave through the star. The shock wave heats and accelerates the outer layers, eventually breaking through the stellar surface and blasting the star apart in a supernova explosion. The energy released in a core collapse supernova is almost incomprehensible. The total energy, mostly carried away by neutrinos, amounts to roughly 3 × 10⁻46 joules more energy than the Sun will radiate in its entire lifetime. The visible light from the supernova, though representing only about 1% of the total energy, still amounts to roughly 10 billion times the Sun's luminosity at peak brightness. For a few weeks, a single exploding star can outshine all the other stars in its host galaxy combined. The material ejected by a supernova expands outwards at velocities of thousands to tens of thousands of kilometers per second, far faster than any spacecraft ever built. This expanding debris, called a supernova remnant, sweeps up the surrounding interstellar medium, creating a growing bubble of hot, shocked gas. The remnant glows at radio, optical, and X-ray wavelengths, remaining visible for tens of thousands of years before finally fading into the general interstellar medium. The Crab Nebula in the constellation Taurus is perhaps the most famous supernova remnant, the expanding debris from a stellar explosion witnessed by Chinese astronomers in the year 1054. At its peak, the supernova was bright enough to be visible in daylight and cast shadows at night, remaining visible to the naked eye for nearly 2 years. Today, the Crab Nebula spans roughly 11 light-years and continues to expand at about 1,500 kilometers per second. At its center lies a pulsar, a rapidly spinning neutron star that emits beams of radiation like a cosmic lighthouse. The supernova of 1054 was a Type II supernova, the core collapse variety that marks the death of a massive star. But there is another type of supernova, designated Type 1a, that arises from a completely different mechanism. Type 1a supernovae occur in binary star systems containing a white dwarf that accretes material from a companion star. As the white dwarf gains mass, it approaches the Chandrasekhar limit. When it crosses this threshold, the white dwarf can no longer support itself against gravity and undergoes a runaway thermonuclear explosion. Unlike core collapse supernova, which leave behind neutron stars or black holes, Type 1a supernova completely destroy the white dwarf, leaving no compact remnant. The entire mass of the star is converted to energy and ejected debris, producing a brilliant explosion that rivals or exceeds the luminosity of core collapse events. Because Type 1a supernovae occur when white dwarfs reach a specific mass threshold, they all have similar peak luminosities, making them useful as standard candles for measuring cosmic distances. The use of Type 1a supernova as distance indicators led to one of the most surprising discoveries in modern cosmology. In the late 1990s, two independent teams of astronomers used distant Type 1a supernovae to measure the expansion rate of the universe at different epochs. They expected to find that the expansion was slowing down, as the gravitational attraction of matter pulled the universe back together. Instead, they found that the expansion is accelerating, the universe is flying apart faster and faster, driven by a mysterious force called dark energy. This discovery, which earned the 2011 Nobel Prize in Physics, revolutionized our understanding of cosmic evolution. Supernovae have been observed throughout human history, though ancient observers did not understand their true nature. Chinese astronomers recorded guest stars appearing suddenly in the sky, shining brightly for weeks or months before fading away. The supernova of 1006, visible in the constellation Lupus, was the brightest stellar event in recorded history, reaching an apparent magnitude of roughly -7.5 bright enough to cast shadows and be visible in daylight. The supernova of 1572, observed by the Danish astronomer Tycho Brahe, helped overturn the ancient belief that the heavens were unchanging and perfect. The most recent supernova visible to the naked eye occurred in 1987, when a star exploded in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, located roughly 160,000 light-years from Earth. Supernova 1987A, as it was designated, was the first supernova visible without a telescope since 1604 and the first to be studied with modern instruments. Neutrino detectors recorded a burst of particles from the collapsing core, confirming theoretical predictions about the supernova mechanism. The expanding remnant continues to be monitored today, providing insights into the physics of supernova explosions and their aftermath. The Milky Way galaxy experiences roughly 2 to 3 supernovae per century, though most are hidden from view by intervening dust and gas. The last supernova definitely observed in our galaxy was Kepler's supernova of 1604, meaning we are statistically overdue for another nearby event. Astronomers monitor several candidate stars that might explode in the relatively near future, including Betelgeuse in Orion and Eta Carinae in the southern constellation Carina. When the next galactic supernova occurs, it will be visible to the naked eye and will provide an unprecedented opportunity to study a stellar explosion up close. The elements produced and dispersed by supernovae are essential for the existence of planets and life. The iron in your blood, the calcium in your bones, the oxygen you breathe, all were forged in the cores of massive stars and scattered across space by supernova explosions. Without supernova, the universe would contain only hydrogen, helium, and trace amounts of lithium, the elements produced in the Big Bang. The heavier elements that make up rocky planets and living organisms exist only because generations of massive stars have lived and died, seeding the cosmos with their nuclear ash. The supernova that contributed to our solar system's formation may have also triggered it. The shockwave from a nearby supernova passing through a molecular cloud could have compressed the gas and initiated the collapse that formed the Sun and planets. Evidence for this scenario comes from the presence of short-lived radioactive isotopes in ancient meteorites isotopes that could only have been produced in a supernova and incorporated into the forming solar system within a few million years of the explosion. We may owe our very existence to the death of a massive star that exploded nearly 5 billion years ago. As we contemplate supernova, we witness the universe at its most violent and creative. These stellar explosions destroy stars but create elements, end one cycle of stellar evolution while enabling the next. The heavy elements dispersed by supernovae become the raw materials for new stars, new planets, and perhaps new life. In the grand cosmic recycling that shapes the universe, Supernovae are the crucial link between stellar death and stellar birth. The mechanism by which the ashes of old stars become the building blocks of new worlds. When a massive star explodes as a supernova, the collapsing core does not simply vanish. If the core mass is between roughly 1.4 and 3 solar masses, the collapse is halted by neutron degeneracy pressure, creating one of the most extreme objects in the universe, a neutron star. These stellar remnants pack more mass than the Sun into a sphere only about 20 kilometers across, achieving densities that exceed those of atomic nuclei and creating conditions unlike anything else in the cosmos. The formation of a neutron star occurs in the final moments of core collapse, when the density becomes so extreme that protons and electrons are forced together to form neutrons. This process, called neutronization or electron capture, releases a flood of neutrinos that carry away most of the gravitational energy of the collapse. The resulting neutron star is composed almost entirely of neutrons, packed together so tightly that the entire object can be thought of as a single giant atomic nucleus. The density of a neutron star defies easy comprehension. A teaspoon of neutron star material would weigh roughly 6 billion tons on Earth, more than the combined mass of every human being who has ever lived. The entire mass of the Sun, compressed into a sphere 20 kilometers across, would have a density of roughly 400 trillion grams per cubic centimeter. At such densities, matter behaves in ways that cannot be replicated in any laboratory, governed by the strong nuclear force and the quantum mechanical properties of degenerate neutron matter. The surface gravity of a neutron star is correspondingly extreme, roughly 200 billion times stronger than Earth's gravity. An object dropped from a height of 1 meter would strike the surface at about 2,000 kilometers per second, releasing as much energy as a small nuclear weapon. The escape velocity from a neutron star surface exceeds 100,000 kilometers per second, roughly 1/3 the speed of light. Light itself is bent by the intense gravitational field, allowing observers to see more than half of the neutron star's surface at once. The structure of a neutron star is thought to consist of several distinct layers. The outer crust, perhaps a kilometer thick, is composed of atomic nuclei arranged in a crystalline lattice, similar to the structure of metals on Earth, but with nuclei far more neutron-rich than any found naturally. Below the crust lies the outer core, a fluid of neutrons with a small admixture of protons and electrons. The inner core, whose composition remains uncertain, may contain exotic forms of matter, such as hyperons, kaon condensates, or even free quarks. Neutron stars are born spinning rapidly, a consequence of the conservation of angular momentum during core collapse. Just as a figure skater spins faster when drawing in their arms, the collapsing core spins up dramatically as it shrinks from Earth size to city size. A newly formed neutron star may rotate hundreds of times per second, though it gradually slows over time as it loses energy to radiation and particle emission. The magnetic fields of neutron stars are among the strongest known in the universe. A typical neutron star has a magnetic field roughly 1 trillion times stronger than Earth's field, concentrated into a volume only 20 kilometers across. These intense fields are inherited from the progenitor star, amplified by the same compression that increases the rotation rate. The magnetic field lines are anchored in the neutron star crust and extend far into space, channeling charged particles and shaping the emission of radiation. The combination of rapid rotation and strong magnetic fields produces one of the most distinctive phenomena associated with neutron stars, the pulsar. A pulsar is a neutron star whose magnetic axis is misaligned with its rotation axis, causing beams of radiation to sweep through space like the beam of a lighthouse. If Earth happens to lie in the path of these beams, we observe regular pulses of radiation as the neutron star rotates, with periods ranging from milliseconds to several seconds. Pulsars were discovered accidentally in 1967 by the British astronomer Jocelyn Bell Burnell, then a graduate student at Cambridge University. While analysing data from a radio telescope designed to study quasars, Bell noticed a regular series of pulses occurring every 1.3 seconds. The signal was so regular that the researchers initially considered the possibility of extraterrestrial intelligence, jokingly designating the source LGM-1 for Little Green Men. Further observations revealed additional pulsars with different periods, confirming that the signals were natural phenomena rather than alien communications. The identification of pulsars as rotating neutron stars came shortly after their discovery, proposed independently by several theorists. The key insight was that no other known object could produce such rapid, regular pulses. White dwarfs are too large to rotate in less than a second without flying apart, and ordinary stars are far too large. Only neutron stars, with their extreme density and compact size, could spin fast enough to explain the observed pulse periods. The Crab pulsar, located at the centre of the Crab Nebula, provides direct evidence linking pulsars to supernova remnants. This pulsar rotates roughly 30 times per second, emitting pulses across the electromagnetic spectrum from radio waves to gamma rays. The pulsar is gradually slowing down, losing rotational energy at a rate that matches the luminosity of the surrounding nebula. The Crab Nebula glows because it is powered by the pulsar at its centre, its light sustained by the rotational energy of the spinning neutron star. The slowing of pulsar rotation, called spin down, occurs because the rotating magnetic field radiates energy into space. This radiation, combined with the emission of charged particles along the magnetic field lines, gradually drains the rotational energy of the neutron star. The rate of spin down can be measured precisely, allowing astronomers to calculate the age of a pulsar and the strength of its magnetic field. Young pulsars spin rapidly and slow down quickly, while old pulsars spin slowly and change little over time. Some pulsars rotate far faster than the Crab pulsar, with periods measured in milliseconds rather than seconds. These millisecond pulsars are thought to be old neutron stars that have been spun up by accreting material from a binary companion. The infalling matter carries angular momentum that is transferred to the neutron star, gradually increasing its rotation rate until it spins hundreds of times per second. The fastest known pulsar rotates 716 times per second, with its surface moving at roughly 1/4 the speed of light. Millisecond pulsars are extraordinarily stable rotators, their periods changing by less than 1 part in a quadrillion per year. This stability makes them useful as cosmic clocks, capable of detecting tiny variations in the fabric of space-time. Arrays of millisecond pulsars are being used to search for gravitational waves ripples in space-time produced by massive objects such as merging supermassive black holes. By monitoring the arrival times of pulses from many pulsars across the sky, astronomers can detect the subtle stretching and squeezing of space caused by passing gravitational waves. The most extreme neutron stars are the magnetars, objects with magnetic fields roughly 1,000 times stronger than typical pulsars. These fields, reaching strengths of 100 trillion to 1 quadrillion times Earth's field, are so intense that they can crack the neutron star crust and trigger powerful bursts of X-rays and gamma rays. Magnetar outbursts can release more energy in a fraction of a second than the Sun emits in 100,000 years, making them among the most energetic events in the universe. The origin of magnetar fields remains somewhat mysterious. One possibility is that they form from the cores of particularly massive or rapidly rotating progenitor stars, which generate stronger fields during collapse. Another possibility is that magnetar fields are amplified by a dynamo process in the first few seconds after the neutron star forms, when the interior is still hot and fluid. Whatever their origin, magnetar fields decay over time, suggesting that magnetars eventually evolve into ordinary pulsars as their fields weaken. Neutron stars in binary systems can accrete material from their companions, producing some of the brightest X-ray sources in the sky. The accreting material spirals inward, forming a disk around the neutron star and heating to temperatures of millions of degrees. The X-rays emitted by this hot gas can be detected by space-based observatories, revealing the presence of neutron stars that would otherwise be invisible. Some accreting neutron stars undergo thermonuclear explosions on their surfaces, as accumulated hydrogen and helium ignite in runaway fusion reactions. The collision of two neutron stars produces one of the most violent events in the universe, releasing enormous amounts of energy in gravitational waves, gamma rays, and visible light. Such a collision was observed for the first time in August 2017, when gravitational wave detectors recorded the inspiral and merger of two neutron stars roughly 130 million light-years from Earth. The event, designated GW170887, was accompanied by a short gamma-ray burst and a visible afterglow that astronomers studied intensively for weeks. The neutron star merger of 2017 confirmed long-standing theoretical predictions about the origin of heavy elements. The collision ejected material rich in neutrons, which rapidly captured additional neutrons to form heavy elements through a process called R-process nucleosynthesis. Spectroscopic observations of the afterglow revealed the signatures of newly formed heavy elements, including gold, platinum, and uranium. A single neutron star merger can produce several Earth masses of gold, making these events the primary source of the heaviest elements in the universe. As we contemplate neutron stars, we encounter matter in its most extreme form, compressed to densities that challenge our understanding of physics. These objects, born in the violent deaths of massive stars, serve as natural laboratories for studying conditions that cannot be replicated on Earth. Their precise pulses provide tools for testing general relativity and detecting gravitational waves. Their mergers forge the heavy elements that make up our world. In their exotic properties and violent behaviors, neutron stars reveal aspects of the universe that would otherwise remain forever hidden. Beyond the neutron star lies an even more extreme fate for the most massive stellar cores. When the collapsing remnant of a supernova exceeds roughly 3 solar masses, not even neutron degeneracy pressure can halt the implosion. The core continues to collapse, shrinking past the point of no return and forming a black hole, a region of space-time so warped that nothing, not even light, can escape. Black holes represent the ultimate triumph of gravity, objects so dense that they punch holes in the fabric of the universe itself. The concept of a black hole emerged from Einstein's general theory of relativity, which describes gravity not as a force, but as the curvature of space-time caused by mass and energy. Shortly after Einstein published his theory in 1915, the German physicist Karl Schwarzschild found an exact solution describing the space-time around a spherical, non-rotating mass. This solution revealed a critical radius, now called the Schwarzschild radius, at which the escape velocity equals the speed of light. Any object compressed within its Schwarzschild radius becomes a black hole, forever cut off from the outside universe. The Schwarzschild radius of an object depends on its mass. For the Sun, The Schwarzschild radius is roughly 3 kilometers. The Sun would need to be compressed to this size to become a black hole. For Earth, the Schwarzschild radius is less than 1 centimeter. For a stellar black hole with 10 times the Sun's mass, the Schwarzschild radius is roughly 30 kilometers. The more massive the black hole, the larger its Schwarzschild radius, though the relationship is linear rather than cubic, meaning that more massive black holes are actually less dense on average. The boundary defined by the Schwarzschild radius is called the event horizon, a one-way membrane that allows matter and light to enter but never to leave. The event horizon is not a physical surface. There is nothing material there that an infalling observer would encounter. Instead, it is a boundary in space-time, a point of no return, beyond which all paths lead inexorably toward a central singularity. An observer falling through the event horizon would notice nothing special at the moment of crossing, though they would be doomed to reach the singularity in a finite time. The singularity at the center of a black hole is a point of infinite density, where the known laws of physics break down. General relativity predicts that all the mass of the black hole is concentrated at this single point, occupying zero volume and possessing infinite density. Most physicists believe that this prediction indicates a failure of general relativity rather than a true physical infinity. A complete theory of quantum gravity, which does not yet exist, would presumably resolve the singularity into something finite and comprehensible. Stellar black holes form when the cores of massive stars collapse at the end of their lives. If the core mass exceeds roughly 3 solar masses, the maximum mass that neutron degeneracy pressure can support, the collapse continues without limit, forming a black hole. The exact boundary between neutron star and black hole formation depends on details of nuclear physics that remain uncertain, but observations suggest that stellar black holes typically have masses between 5 and 20 solar masses. The formation of a stellar black hole may or may not be accompanied by a supernova explosion. In some cases, the collapsing core may swallow the shock wave that would otherwise blow the star apart, causing the entire star to implode directly into the black hole. These failed supernovae would produce no visible explosion, only the sudden disappearance of a massive star. Astronomers have identified several candidate failed supernovae by searching for massive stars that have vanished without producing detectable explosions. Black holes are often described as cosmic vacuum cleaners, sucking in everything around them. This description is misleading. A black hole's gravitational influence extends no farther than that of any other object with the same mass. If the Sun were magically replaced by a black hole of equal mass, the planets would continue orbiting exactly as before. They would just be orbiting in darkness. Black holes are dangerous only to objects that approach very close to the event horizon, within a few Schwarzschild radii of the center. Material falling toward a black hole does not simply plunge straight in. Conservation of angular momentum causes the infalling matter to spiral inward, forming a rotating disk called an accretion disk. As material in the disk spirals closer to the black hole, it speeds up and heats up, reaching temperatures of millions of degrees in the innermost regions. This hot gas emits copious X-rays, making accreting black holes among the brightest X-ray sources in the sky. The first strong candidate for a stellar black hole was Cygnus X1, an X-ray source in the constellation Cygnus discovered in 1964. Observations revealed that the X-rays come from a binary system in which an invisible compact object is accreting material from a blue supergiant companion. The mass of the compact object, determined from the orbital motion of the visible star, exceeds 20 solar masses, far too heavy to be a neutron star. Cygnus X1 remains one of the best studied stellar black holes. Its properties refined by decades of observations across the electromagnetic spectrum. The detection of gravitational waves has opened a new window on stellar black holes. When two black holes orbit each other, they emit gravitational waves that carry away energy, causing the orbit to shrink. Eventually, the black holes spiral together and merge, producing a final burst of gravitational waves that can be detected by instruments on Earth. The first direct detection of gravitational waves, announced in February 2016, came from the merger of two black holes roughly 30 times the mass of our Sun, circling each other at close to the speed of light before fusing in a collision that released an enormous amount of energy, equivalent to about 3 solar masses. This event, detected on September 14, 2015, by the Laser Interferometer Gravitational Wave Observatory, marked one of humanity's greatest scientific achievements and confirmed a key prediction of Einstein's general theory of relativity. The gravitational waves from this first detection, designated GW 1509-4, travelled for roughly 1.3 billion years before reaching Earth. By the time they arrived, the waves had been stretched by the expansion of the universe and weakened by their journey across cosmic distances. The distortion they produced in the LIGO detectors was incredibly small, roughly 1,000th the diameter of a proton. Yet this minuscule signal was enough to reveal the violent merger of two black holes that occurred when multicellular life on Earth was just beginning to evolve. The process that leads to a black hole merger unfolds over vast timescales. Two black holes in a binary system orbit each other, radiating gravitational waves that carry away some of the system's orbital energy. Over millennia, this causes the objects to move closer and closer together. The closer they are, the faster they orbit each other, which causes them to radiate stronger gravitational waves, which causes them to lose more orbital energy. The objects are locked in a runaway, accelerating, spiraling embrace, doomed to eventual collision. The final moments of a black hole merger are extraordinarily violent. In the last fraction of a second, the two black holes complete hundreds of orbits, moving at significant fractions of the speed of light. The gravitational waves emitted during this inspiral phase sweep upward in frequency, producing a characteristic chirp that encodes information about the masses and spins of the merging objects. When the black holes finally touch, they merge into a single, larger black hole, which then settles down by emitting additional gravitational waves in a process called ring-down. Since that first detection, gravitational wave observatories have recorded dozens of black hole mergers, revealing a population of stellar black holes that was previously invisible. These observations have shown that stellar black holes can be more massive than previously thought, with some exceeding 50 or even 80 solar masses. The origin of these heavy black holes remains uncertain. They may form from the collapse of very massive stars in low metallicity environments, or they may grow through successive mergers in dense stellar environments, such as globular clusters. The gravitational wave observations have also revealed black holes in the so-called mass gap between roughly 2 and 5 solar masses, a range where few black holes were expected based on theoretical models of stellar evolution. The existence of these intermediate mass objects challenges our understanding of how massive stars die and suggests that the boundary between neutron star and black hole formation may be more complex than previously appreciated. Beyond stellar black holes, the universe contains far more massive specimens. Supermassive black holes, with masses ranging from millions to billions of solar masses, lurk at the centres of most large galaxies. These cosmic behemoths are not formed from the collapse of individual stars, but rather grow over cosmic time through the accretion of gas and the merger of smaller black holes. The supermassive black hole at the centre of our own Milky Way, called Sagittarius A, has a mass of roughly 4 million solar masses and occupies a region smaller than the orbit of Mercury. The existence of Sagittarius A was inferred from observations of stars orbiting the galactic centre. These stars, tracked over decades using adaptive optics on large ground-based telescopes, follow elliptical orbits around an invisible point mass. The closest approach of one star, called S2, brings it within about 17 light-hours of the central object, moving at roughly 3% of the speed of light. The orbital parameters of S2 and other stars provide a precise measurement of the central mass, confirming the presence of a supermassive black hole. In April 2019, the Event Horizon Telescope collaboration released the first direct image of a black hole, or rather, of the shadow cast by a black hole against the glowing gas surrounding it. The target was the supermassive black hole at the centre of the galaxy M87, a giant elliptical galaxy roughly 55 million light-years from Earth. The image shows a bright ring of emission surrounding a dark central region, the shadow of the event horizon, silhouetted against the hot accretion flow. This image, constructed from radio observations made by telescopes spanning the globe, provided direct visual evidence for the existence of black holes. A second image, released in 2022, showed Sagittarius A, the supermassive black hole at the centre of our own galaxy. This image was more challenging to produce because Sagittarius A is much smaller than the M87 black hole and varies on timescales of minutes rather than days. The resulting image shows a similar ring and shadow structure, confirming that the object at the galactic centre is indeed a black hole, with properties consistent with general relativity. The environments around supermassive black holes can be extraordinarily energetic. When large amounts of gas fall toward a supermassive black hole, the accretion disk can outshine the entire host galaxy, producing what astronomers call an active galactic nucleus. The most luminous active galactic nuclei, called quasars, can be seen across billions of light-years. Their light powered by the gravitational energy of matter, spiralling into the central black hole. A single quasar can emit more energy than 1 trillion suns, making them among the most luminous objects in the universe. Some active galactic nuclei produce powerful jets of material that shoot outward from the poles of the accretion disk at nearly the speed of light. These jets, collimated by magnetic fields threading the disk, can extend for hundreds of thousands of light-years, far beyond the boundaries of the host galaxy. The jets carry enormous amounts of energy into intergalactic space, heating the surrounding gas and influencing the evolution of galaxy clusters. The mechanism that launches and collimates these jets remains an active area of research, though magnetic fields anchored in the spinning black hole are thought to play a crucial role. The relationship between supermassive black holes and their host galaxies is one of the most intriguing puzzles in modern astrophysics. Observations have revealed tight correlations between black hole mass and various properties of the host galaxy, such as the mass of the central bulge and the velocity dispersion of stars. These correlations suggest that black holes and galaxies evolve together, each influencing the other's growth through feedback processes that are not yet fully understood. One proposed feedback mechanism involves the energy released by active galactic nuclei. When a supermassive black hole is actively accreting, the radiation and jets it produces can heat the surrounding gas, preventing it from cooling and forming new stars. This negative feedback may explain why the most massive galaxies have stopped forming stars, their gas supplies kept hot by the central black hole. Conversely, when the black hole is quiescent, gas can cool and flow inward, potentially triggering new episodes of accretion and star formation. The origin of supermassive black holes remains mysterious. The most distant quasars, seen as they were less than 1 billion years after the Big Bang, already contain black holes with masses of billions of solar masses. Growing such massive objects in such a short time is challenging. Even continuous accretion at the maximum possible rate would struggle to produce billion solar mass black holes within the available time. Various scenarios have been proposed, including the direct collapse of massive gas clouds into seed black holes, the rapid growth of stellar mass black holes in dense environments, and the merger of intermediate mass black holes formed in the first generation of stars. Between stellar black holes and supermassive black holes lies a poorly explored regime of intermediate mass black holes, with masses ranging from hundreds to hundreds of thousands of solar masses. These objects are difficult to detect because they are too small to produce the dramatic effects of supermassive black holes, and too rare to be found in large numbers like stellar black holes. However, gravitational wave observations have begun to reveal black holes in this intermediate range, formed through the merger of smaller black holes in dense stellar environments. The physics of black holes touches on some of the deepest questions in science. The information paradox, first articulated by Stephen Hawking in the 1970s, asks what happens to information about objects that fall into a black hole. Quantum mechanics insists that information cannot be destroyed, yet the classical picture of a black hole suggests that anything crossing the event horizon is lost forever. Resolving this paradox may require a complete theory of quantum gravity, which would unite general relativity with quantum mechanics and potentially reveal the true nature of the singularity at a black hole's centre. Hawking also showed that black holes are not entirely black. They emit a faint glow of thermal radiation due to quantum effects near the event horizon. This Hawking radiation causes black holes to slowly evaporate over time, losing mass and eventually disappearing entirely. For stellar and supermassive black holes, this evaporation is negligibly slow. A stellar black hole would take far longer than the current age of the universe to evaporate. But in the far future, when all other sources of light have faded, the slow evaporation of black holes may be the last source of energy in a dying cosmos. As we contemplate black holes, we encounter the universe at its most extreme and mysterious. These objects, predicted by Einstein's equations more than a century ago, have been confirmed by observations ranging from X-ray telescopes to gravitational wave detectors to planet-spanning radio arrays. They challenge our understanding of space, time, and the nature of reality itself. In their darkness, they illuminate the deepest questions about the universe we inhabit. The atoms that compose your body, the air you breathe, the ground beneath your feet, all were forged in the hearts of stars. This profound truth, one of the great discoveries of 20th century science, connects us intimately to the cosmos. We are not merely observers of the universe, we are participants in its grand chemical evolution, made of atoms that were once part of stellar cores, supernova explosions, and neutron star collisions. The story of how stars create elements is the story of how the universe became capable of producing planets, life, and minds that can contemplate their own origins. In the beginning, the universe contained only the simplest elements. The Big Bang, occurring roughly 13.8 billion years ago, produced a cosmos composed almost entirely of hydrogen and helium, with trace amounts of lithium and beryllium. These light elements formed in the first few minutes after the Big Bang, when the universe was hot and dense enough for nuclear reactions to occur. But the expansion and cooling of the universe quickly shut down this primordial nucleosynthesis, leaving a cosmos devoid of the heavier elements that would later prove essential for rocky planets and living organisms. The first stars to form, perhaps 200 million years after the Big Bang, were composed entirely of this primordial material. These population 3 stars, as astronomers call them, have never been directly observed, but theoretical models suggest they were massive and short-lived, burning through their hydrogen fuel in just a few million years. When they died, they produced the first heavy elements, seeding the universe with carbon, oxygen, and other products of stellar nucleosynthesis. The process of element creation in stars begins with hydrogen fusion, the reaction that powers main sequence stars like our Sun. As we have seen, this process converts hydrogen into helium, releasing energy that sustains the star against gravitational collapse. But hydrogen fusion is just the first step in a long chain of nuclear reactions that can build progressively heavier elements. When a star exhausts the hydrogen in its core and begins burning helium, the triple alpha process creates carbon by fusing 3 helium nuclei together. This reaction is remarkably sensitive to the properties of the carbon nucleus. If the energy levels of carbon were slightly different, the reaction would proceed too slowly to produce significant amounts of the element. The fact that carbon exists in abundance throughout the universe depends on a seeming coincidence in nuclear physics, a coincidence that the astronomer Fred Hoyle famously predicted before it was experimentally confirmed. Some of the carbon produced by helium burning captures additional helium nuclei to form oxygen, another element essential for life as we know it. The ratio of carbon to oxygen produced depends on the details of the nuclear reactions and the conditions in the stellar core. In most stars, oxygen is somewhat more abundant than carbon, though the exact ratio varies. Both elements are ejected into space when the star dies, either through stellar winds during the giant phase or through supernova explosions. More massive stars continue the chain of nuclear burning beyond helium, fusing carbon, neon, oxygen, and silicon in successive stages. Each stage produces heavier elements and lasts for a shorter time than the previous one. Carbon burning produces neon, sodium, and magnesium. Neon burning produces oxygen and magnesium. Oxygen burning produces silicon, sulfur, and other intermediate mass elements. And silicon burning produces iron and related elements, the end of the line for fusion reactions that release energy. The products of these successive burning stages accumulate in layers around the stellar core, creating the onion-like structure characteristic of massive stars in their final stages. The outermost layer contains unburned hydrogen, followed by layers of helium, carbon, oxygen, neon, silicon, and finally an iron core at the center. When the star explodes as a supernova, these layers are ejected into space, enriching the interstellar medium with the full range of elements produced by stellar nucleosynthesis. But the elements produced by fusion in stellar cores represent only part of the periodic table. Elements heavier than iron cannot be produced by fusion reactions that release energy. Creating these elements requires an input of energy rather than a release. The universe has found 2 main pathways for producing these heavy elements, both involving the capture of neutrons by atomic nuclei. The slow neutron capture process, called the S process, occurs in the outer layers of asymptotic giant branch stars. In these evolved stars, helium shell flashes periodically release bursts of neutrons, which are captured by iron and other seed nuclei. The neutron capture occurs slowly enough that unstable nuclei have time to undergo beta decay before capturing additional neutrons, producing a characteristic pattern of isotopes along the valley of nuclear stability. The S process is responsible for roughly half of the elements heavier than iron, including strontium, barium, and lead. The rapid neutron capture process, called the R process, occurs in environments with extremely high neutron densities. where nuclei capture neutrons faster than they can decay. For decades, the site of the R process remained uncertain, with core collapse supernova and neutron star mergers both proposed as candidates. The neutron star merger observed in 2017, designated GW1087, provided direct evidence that these events are major sites of R-process nucleosynthesis. Spectroscopic observations of the merger afterglow revealed the signatures of newly formed heavy elements, confirming that neutron star collisions produce significant quantities of gold, platinum, uranium, and other R-process elements. The gold in a wedding ring, the platinum in a catalytic converter, the uranium in a nuclear reactor ore were forged in the violent collisions of neutron stars, scattered across space by the explosions that followed, and eventually incorporated into the gas cloud that formed our solar system. A single neutron star merger can produce several Earth masses of gold, along with comparable amounts of other precious metals. These elements, rare on Earth, are rare precisely because the events that create them are rare. Neutron star mergers occur only a few times per million years in a typical galaxy. The chemical evolution of the universe is a story of gradual enrichment, as successive generations of stars produce heavy elements and return them to the interstellar medium. The first stars formed from pristine primordial gas, containing only hydrogen and helium. When these stars died, they enriched their surroundings with the first heavy elements. The next generation of stars formed from this enriched gas, incorporating small amounts of carbon, oxygen, and other elements into their composition. Each subsequent generation incorporated more heavy elements, gradually increasing the metallicity of the universe. Astronomers can trace this chemical evolution by measuring the compositions of stars of different ages. The oldest stars in the galaxy, found in the halo and in globular clusters, have very low metallicities. Some contain less than 1/1000th the heavy element abundance of the Sun. These ancient stars formed early in the galaxy's history, before many generations of stellar nucleosynthesis had enriched the interstellar medium. Younger stars, like the Sun, have higher metallicities reflecting the accumulated contributions of billions of years of stellar evolution. The Sun itself contains about 2% heavy elements by mass, a composition inherited from the gas cloud that formed the solar system roughly 4.6 billion years ago. This modest heavy element fraction was sufficient to form the rocky planets of the inner solar system, including Earth. Without the heavy elements produced by previous generations of stars, there would be no silicon for rocks, no iron for planetary cores, no carbon for organic molecules. The existence of Earth and everything on it depends on the nuclear alchemy that occurred in stars that lived and died before the Sun was born. The distribution of elements in the solar system provides clues to the specific events that contributed to its formation. The presence of short-lived radioactive isotopes in ancient meteorites indicates that a supernova or other nucleosynthetic event occurred shortly before the solar system formed, injecting freshly synthesized material into the collapsing cloud. Some researchers have proposed that the shockwave from this event may have triggered the collapse itself, making the supernova not just a contributor of heavy elements, but also the initiator of solar system formation. The carbon in your body was produced by helium fusion in the core of a red giant star, ejected into space when the star shed its outer layers as a planetary nebula. The oxygen you breathe was forged in the later stages of massive star evolution, released in a supernova explosion that scattered the star's remains across light years of space. The iron in your blood was produced in the final moments of silicon burning, just before the core collapsed and the star exploded. The calcium in your bones, the phosphorus in your DNA, the trace elements that enable the chemistry of life, all have similar stellar origins. This cosmic perspective on our chemical composition was eloquently expressed by the astronomer Carl Sagan, who noted that we are made of star stuff. The phrase captures a profound truth. The atoms in our bodies have histories stretching back billions of years. Through multiple generations of stars, supernovae, and cosmic recycling, we are not separate from the universe but intimately connected to it. Our very substance forged in the nuclear furnaces of long-dead stars. The ongoing process of stellar nucleosynthesis continues to enrich the universe with heavy elements. Every supernova that explodes, every neutron star merger that occurs, every planetary nebula that forms adds to the cosmic inventory of elements. The metallicity of the universe is slowly increasing, though the rate of increase has slowed as star formation has declined from its peak billions of years ago. Future generations of stars will form from gas that is slightly more enriched than the gas that formed the Sun, continuing the gradual chemical evolution that has been proceeding since the first stars ignited. In the far future, when the last stars have burned out and the universe has grown dark and cold, the heavy elements produced by stellar nucleosynthesis will remain. These atoms, forged in stellar cores and scattered by stellar deaths, will persist as the permanent legacy of the stellar era. They will drift through the void, perhaps occasionally coming together to form new structures, but never again participating in the nuclear reactions that created them. The story of stellar alchemy will have ended, but its products will endure for eternity. As we contemplate the origin of the elements, we gain a new appreciation for our place in the cosmos. The universe has spent billions of years preparing the ingredients for planets and life, cooking heavy elements in stellar furnaces and distributing them through space. We are the beneficiaries of this cosmic chemistry, our existence made possible by processes that began long before Earth formed and will continue long after our species has vanished. In understanding stellar nucleosynthesis, we understand something fundamental about ourselves. We are children of the stars, made of atoms that have journeyed across space and time to become part of us, closing the eternal cycle. And so we come to the end of our journey through the story of stars, from their gentle births in cold molecular clouds to their dramatic deaths as supernovae, white dwarfs, neutron stars, and black holes. We have travelled across scales of space and time that dwarf human experience, from the subatomic realm of nuclear fusion to the cosmic expanses where galaxies drift like islands in an infinite sea. We have witnessed the patient accumulation of matter under gravity's gentle pull, the ignition of nuclear fires that sustain stellar luminosity for billions of years, and the violent explosions that scatter heavy elements across the cosmos. The story of stars is in many ways the story of the universe itself. Stars are the engines of cosmic evolution, transforming the simple hydrogen and helium of the early universe into the rich diversity of elements that make planets and life possible. They are the sources of light that illuminate the darkness, the forges where atoms are transmuted, the crucibles where the raw materials of existence are refined. Without stars, the universe would be a cold, dark, chemically impoverished place, devoid of the complexity that makes our existence possible. Yet the story of stars is also a story of cycles and renewal. The matter that forms the star does not disappear when the star dies. It is returned to the interstellar medium, enriched with heavy elements and ready to participate in the formation of new stars. The gas expelled by planetary nebulae, the debris scattered by supernovae, the material ejected by stellar winds. All of this matter eventually finds its way into new molecular clouds, new stellar nurseries, new generations of stars. The universe recycles its matter endlessly, each cycle adding to the chemical complexity of the cosmos. Our own sun is a product of this cosmic recycling, formed from gas that had been processed through multiple generations of stars. The heavy elements in the solar system, the silicon and iron of rocky planets, the carbon and oxygen of organic molecules, the gold and uranium of neutron star mergers, all were contributed by stars that lived and died before the sun was born. We are part of this cycle, our bodies composed of atoms that have journeyed through stellar cores and supernova explosions to become part of us. The stars that shine into night sky are at various stages of this eternal cycle. Some are young, newly emerged from their natal clouds and just beginning their long lives on the main sequence. Others are middle-aged, like our sun, steadily burning hydrogen and providing stable environments for any planets that orbit them. Still others are old, swelling into red giants or collapsing into white dwarfs, approaching the ends of their stellar lives. And somewhere in the galaxy, at this very moment, new stars are being born, continuing the cycle that has been proceeding for more than 13 billion years. The future of this cycle stretches far beyond human comprehension. Stars will continue to form for trillions of years, though the rate of formation will gradually decline as the galaxy's gas supply is exhausted. The last stars to form will be red dwarfs, small and dim but extraordinarily long-lived, burning their hydrogen fuel for periods that exceed the current age of the universe by factors of hundreds or thousands. These final stars will shine on long after the great blue giants have exploded and faded, the last sources of starlight in an aging cosmos. Eventually, even the red dwarfs will exhaust their fuel and fade into darkness. The universe will enter an era of stellar remnants, white dwarfs cooling toward absolute zero, neutron stars spinning down and growing cold, black holes slowly evaporating through Hawking radiation. The era of starlight will have ended, giving way to an epoch of darkness that will last far longer than the stellar era that preceded it. But that distant future need not concern us tonight. For now, the stars continue to shine, their light travelling across the void to reach our eyes and fill us with wonder. Each point of light in the night sky represents a sun, perhaps with planets of its own, certainly with a story of birth, life, and eventual death. The stars connect us to the cosmos, reminding us that we are part of something far larger than ourselves, participants in a grand cosmic drama that has been unfolding for billions of years. As you drift towards sleep, let the stars be your companions. Imagine the molecular clouds where new stars are forming, the gentle collapse of gas and dust under gravity's patient pull. Picture the nuclear fires burning in stellar cores, the steady conversion of hydrogen to helium that sustains stellar luminosity across the ages. Envision the red giants swelling to enormous dimensions, the planetary nebulae glowing with the light of ionized gas, the supernova exploding with the brilliance of billions of suns. The universe is vast and ancient, filled with wonders beyond counting. The stars are our guides to this cosmic immensity, beacons of light that have inspired human wonder since the first members of our species gazed upward at the night sky. They will continue to shine long after we are gone, their light carrying the story of cosmic evolution to any beings who might observe them in the distant future. Rest now, beneath the canopy of stars. Let their ancient light wash over you, connecting you to the cosmos that gave you birth. You are made of star stuff, your atoms forged in stellar cores and scattered across space by stellar deaths. In contemplating the stars, you contemplate your own origins, your own place in the grand story of the universe. The stars will keep their vigil while you sleep, burning steadily through the night, continuing the cycles of birth, life, and death that have shaped the cosmos since the beginning of time. And when you wake, they will still be there, hidden by the light of our own star, but no less present, no less wondrous, no less connected to the deepest truths about the universe and our place within it. Sweet dreams, fellow traveller among the stars.